Okay,
Yeah, go ahead.
awesome. Hello, everyone. Welcome to our tutorial on physics-based rendering and its applications in computational photography and imaging. I'm Aditya Pedredla. I'm currently an assistant professor at Dartmouth College, though most of this work was done during my time at Carnegie Mellon University. Yanis Giolakas here is the second speaker. He's my mentor during my time at Carnegie Mellon University. I guess that's a lifetime appointment, so it's a lifetime mentor for me. Yanis is going to give a introduction to physics-based rendering, and then I'm going to talk about various physics-based rendering techniques that we have developed and are also developed in the recent past, and we'll see their applications to various computational imaging and computational photography techniques. Thank you. Go ahead, Yanis.
All right. Hello, everyone. As I said, my name is Yanis Giolakas. So then what this tutorial is about, it's really about, computational imaging. And that's an area that's made up of, it's at the intersection of a lot of different other areas, because there is computer vision, which is why this tutorial is here at CVPR, where computational imaging draws a lot of ideas from geometry processing, different features, optical flow techniques, learning-based techniques, and so on. There are optics, where we have to play around with different types of sensors, different types of physical models, designing lenses, designing different combinations of all of these components. Image processing, where we work together, we work along with different transformations, filtering, compression algorithms, linear models, forward and inverse, and of course, computer graphics, where we have to use rendering, light transfer, different material models, AR, VR, and so on. So the intersection of all of this is computational imaging, right? So what we want to do today is emphasize one aspect of this Venn diagram, which is the role of computer graphics in computational imaging, and specifically a subpart of this Venn diagram, which is rendering. So how physics-based rendering techniques, which are encountered in vision and graphics in a lot of flavors, can help specifically for computational imaging. And we'll do that in the context of the following structure. So we'll go over different types, two core different types of rendering. One is forward rendering applications, where we are given some sort of scene specification. There may be some material, a type of sensor we are using to image that material, imaging lighting conditions, and so on. And we want to synthesize for that scene photorealistic images. And inverse rendering application, where, as the name suggests, we're doing the opposite pipeline. We're given images that may come either from actual measurements or from some design target that someone provides us. And from that, we can come up with either unknown scene information, material parameters, geometry, and so on, or unknown sensor information. And we'll introduce different advances in the context of these two broad categorizations of rendering for a few different computational imaging applications. These include, for the forward rendering side, time-of-flight imaging, how we can use forward rendering techniques to design new time-of-flight sensors and their applications to inverse problems such as non-sight imaging, 3D sensing, LiDAR, and so on. Second, acousto-optic imaging. So this is an area of imaging that is very common in medical settings, where we take advantage of the interaction of sound and light to create new imaging capabilities. And again, we'll see how we can create forward rendering algorithms tailored to this imaging problem, and then how to use these rendering algorithms to actually make advances in acousto-optic imaging. Ultra-fast light scanning, again, an emerging area in optics design, where we play with, once again, the interplay with sound and light, and again, see how rendering in this case can help us simulate new devices and design very fast optical devices, optics devices actually, that combine sound and light. Speckle imaging, so see how we can extend physics-based rendering algorithms to handle wave effects such as speckle, and then use those in applications like fluorescence microscopy, tissue imaging, imaging through scattering, and so on. Tactile sensor design, so again, same pipeline, see how we can use specialized rendering algorithms to simulate specific types of tactile sensors that are based on light, and then optimize those for different robotics manipulations, such as manipulation, identification of text, and so on. And then on the inverse side, discuss many advances on a specific class of rendering algorithms called differentiable rendering that allow us to, well, as the name suggests, differentiate through a simulator of light transport, and there's utility for inverse problems. All right. Now, before we dive into any of these specific techniques, I want to give a very short background about rendering, and in particular about the type of rendering that we will mostly be concerned with in this tutorial. And this is something that I like to call physics-based rendering, because it gives us the ability to produce photorealistic images, even in scenes we have very complex light transport effects. So what do we mean by that? By complex light transport effects, I mean a lot of the things that we see in a photograph like this, where we have some incident light come into the scene, in this case from sun outside the window. And then as this light interacts with different materials and different objects inside the scene, we can have effects such as indirect light appear in different parts of the scene, cast shadows, indirect shadows, shadows that would not be there if we didn't have multiple interactions of light. We can have caustics, very complex, very high frequency reflections created by the interaction of light with specular objects. We can have interreflections, glossy or specular, or diffusing the reflections that are due to light bouncing several times. Or we can even have volumetric scatterings. So light that travels inside materials and therefore can produce very different types of appearances. So we are concerned with algorithms that can efficiently reproduce all of these types of effects. And in fact, throughout the tutorial, we'll see how we can generalize these algorithms to capture more and more complex light material interactions, like acoustoptic effects, speckle, and so on. And I'm going to give a very brief introduction about how these physics-based rendering algorithms that we'll mostly cover work. And at the core of all of these algorithms is a theory from computer graphics called the path integral form of light transport. Now, I've thrown there a complex-looking integral. It's not really that bad if we try to break it down into exactly what's into the different terms. So we have an integral here for expressing the image that a sensor, and by sensor I really mean any kind of device that measures light, captures. So what is this integral over? It's an integral over all of the different light paths, all of the different, basically piecewise linear paths that light can follow in a scene. So this can include a reflection with different objects, or in the case of volumetric scattering, propagation inside materials. And these light paths start at a sensor and end at a light source. Typically in physics-based rendering, we work with light propagation in the inverse direction, starting in the sensor, going to the source. And then what do we do for each of these light paths? For each one of them, we form a weighted contribution. We try to figure out how much they contribute to the measurement that our sensor captures. And this contribution has three terms. There is the weight sensor. Basically, it says how important is this path for my sensor. For example, for a camera, for a perspective camera, I know that I only care about light paths that pass through the pinhole of that camera. For an orthographic camera, I only care about light paths that hit that sensor in a specific direction. For other types of sensors, which can be LiDAR, which can be time of flight, I care about specific types of light paths like Aditya will discuss. There is correspondingly a source weight that basically says how much light did this path, how much flux to be precise, did this path draw out of a light source in a scene. And then there is another term in between that says how does this flux travel through the scene along the path to go from the light source to the sensor. And then this path throughput has a complex term, a complicated form that's basically multiple products of reflection events, BSDFs, and also some other term we call the geometry that basically says how radiance or how flux propagates from one point along a path to another. Okay, so complex looking equation that's nothing else but I want to figure out all of the types of paths, all of the types of piecewise linear paths in this scene, and compute the flow of light along them from a light source to the sensor. Now, this is a nice mathematical model. How do we actually evaluate that in practice to simulate an image? We cannot enumerate all light paths. Nature can do that. Light travels super fast, but we don't have fast enough machines to do that. So how do we come up with something that's tractable, something that's computationally efficient, we use a type of algorithms called Monte Carlo rendering. And at a high level, what these do is say that I will approximate this integral I showed here with a sum that's also over different paths. But instead of trying to enumerate all of the possible different paths in a scene, I will just use a few that I randomly select. Okay. Now, what do I have here in this summation? There is at the top exactly the same path contribution I had earlier in the integral expression. And then at the bottom, there is the PDF, the probability distribution that I use to sample this path. Now, what is this PDF and where do these randomly sampled paths come from? Effectively, all of the algorithms that you may have heard of for physics-based rendering, like path tracing, ray tracing, bidirectional path tracing, Markov chain, Monte Carlo, and so on, you can view them as ways to sample random paths like that. So the high level, path tracing says that I will sample paths starting from the sensor. I'll draw a ray from the sensor, I will hit some part in the scene, do a reflection, hit another part in the scene, do another reflection, and keep going until I reach a light source. There is light tracing that does the opposite. I will start from a light source, draw a ray, hit a part in the scene, do a reflection, hit another part in the scene, and so on. Or I can start playing more complex combinations of this. I can do something called bidirectional path tracing, where I start half of my path or part of my path from a sensor, I start the other path from the light source, and then I combine them. And really, in all of this, what we are trying to do is come up with algorithms such that the PDF of the path is approximate, maximizes, will sample with very high probability paths that have very strong contributions to our images. Okay, so these are the kinds of algorithms that we will be mostly talking about. And again, everything I've presented so far is standard background physics-based rendering. What we'll mostly be focusing on how we can extend these kinds of algorithms we can find implemented in PBRT or in Tuba or Unreal Engine or many other graphics engines for scientific imaging applications to make it possible to both simulate more and more advanced types of cameras, types of sensors, and also solve more complex design and inverse problems. All right, so hand it over to Aditya.
Thank you, Yanis, for the introduction. So we saw how path space rendering works in general for intensity cameras. So what we are going to see next is how we can extend this path space formulation to non-conventional cameras, such as time-of-flight cameras or acousto-optics or spectral or render physical effects of light that are typically not modeled in graphics, like the wave effects of light. These are the things that we are going to see next. And we'll start with
maybe something to say is that if people want to ask questions, you're welcome to come up to the mic, even during the presentation, and ask us. So don't wait until the coffee break or anything. And or also, if you're attending via Zoom, you can post in the chat, and then I'll try to relay that question to the teacher. Okay?
Yeah, sounds good. Thank you, Yanis. Yeah, please feel free to interrupt me. I actually like that that when people interact with me and it's not a one-way lecture. So for those of you who don't know what time-of-flight cameras are, so time-of-flight cameras are the cameras that measure not just the intensity of light, but they measure the time-resolved radiance. So in this particular video, a laser pulse is fired from one end of this Coke bottle, and the laser pulse is traveling through the Coke bottle, scattering multiple times, and is reaching to the camera. And what Andreas Welton and his colleagues did were they captured it. They captured this light in some sense at the speed of light and were playing it down very, very slowly. So time-of-flight cameras, the specific time-of-flight camera is called transient camera. They bin light based on their total time of travel. So let us understand what is happening from the path space perspective. So when we fire a laser pulse from the light source, the photons take multiple random paths before reaching the camera. All these light paths have different optical path lengths. The time-of-flight camera used by Welton et al. Bins these light paths based on the optical path length. And these cameras, like I said, are transient time-of-flight cameras. We have several time-of-flight cameras in the market, and they all bin light paths very differently. based on how they bin the light paths, we can classify them into continuous wave, transient, we just saw how transient cameras work, and time-gated cameras. And we will see how we can build or simulate or render, build simulators or rendering techniques for all these time-of-flight cameras, not just one of them, but all of them. And before that, what I'm going to do is I will jump ahead and show the renderings to explain about all these three different kinds of time-of-flight cameras. Okay, for that, I took this scene. On the left, you can see the Cornell box scene. It has like two boxes inside a room and a light source on the top. And this is how an intensity camera, the camera that is there on the webcam or my phone camera or DSLR is going to capture the Cornell box scene, and that's how it's going to look like. A continuous wave time-of-flight camera, such as the one that is found in your Xbox, it's going to weigh the light paths with a sinusoidal weight before summing them up. So it's going to take all the light paths, take their optical path lengths, weigh these light paths contribution with a sinusoidal weight on the path length, and then it's going to sum them up. That's how a continuous wave time-of-flight camera is going to work. And a transient camera just bins photons based on their time of travel. The Coke bottle video that I have shown is actually an example of a transient camera. A time-gated camera accepts photons whose total time of travel is within a narrow time length range. So it's going to basically accept photons which took a total time of travel to be approximately constant, and it rejects all other photons. You can think of time-gated camera at a high level in a loose manner, as if it's a slice of this transient camera. Okay, but they are actually in a hardware, they are implemented very, very differently. Now, the path space integral for intensity cameras that we have learned can be extended to time-of-flight cameras. Yeah.
You said for the continuous wave time-of-flight, the rate is a sinusoid.
Yes.
Is there a specific reason for it?
Yeah. So the cameras that the thing is, it can be programmed, but it's typically a continuous wave. Like it can be sinusoidal, it can be rectangular, triangular, square, trapezoidal. There are other shapes that people have experimented, but it cannot be a very, very narrow range time gate. It's typically like smooth for all the regions. And for continuous wave, I mean, I don't want to go into the deep math of why it is sinusoidal and all, but taking like quadrature measurements, since you work on holography, you can, just like the wave, you can, using Michelson's interferometry, you can compute the phase. If you do a sinusoidal modulation, you can actually compute the depth with continuous wave time-of-flight camera. That's why people use sinusoidal modulation. Yeah. Thank you for the question. So the path space integral, like I was saying, that we built for intensity cameras, which is simply saying that take all the light paths, take their contributions, the path contributions, and sum them up, right? And that gives you your image. That's what the path space integral here is saying. This can be extended to time-of-flight cameras also, and let's see how we can do that. Before that, just to recollect, we solved the path space integral with Monte Carlo rendering by randomly sampling the light paths, either using light tracing or path tracing or bidirectional path tracing. And we approximate the image with this summation, right? Sample random paths and then take the ratio of path contribution to the probability of the path and do that for many, many paths and take the average of that, and that gives you that average of that, and that gives you the image. Okay, so the time-of-flight cameras, all they do is they weigh light paths based on a function that depends on the camera and optical path length. So all we need to do to get the path space integral for time-of-flight cameras is take this intensity integral, multiply it with a path length weighing function. This path length weighing function changes based on what time-of-flight camera we have, and that gives us the time-of-flight image. Okay, so the Monte Carlo techniques that we have built for intensity cameras, they can be extended to time-of-flight cameras easily by simply multiplying with the path length weighing function, right? Does that make sense? So for a continuous wave time-of-flight camera, like we saw earlier, it's going to be a sinusoidal path length weighing function, right? And these parameters will change based on what camera you are using and all. And this is how the rendered image will look like. And for a time-gated camera that uses narrow weighing function with a very narrow support, corresponding to the fact that it accepts only photons coming from a narrow optical time of flight, the image is going to look something like this. And finally, for a transient camera, it's like an extension to time-gated camera. That's another way to see transient cameras, where we capture not just one gate, but we are capturing many gates, all the time gates, and we get a transient video. The path sampling techniques like light tracing or path tracing or bidirectional path tracing that were built for intensity cameras remain efficient for 2 out of the 3 time of flight cameras, namely the continuous wave time of flight camera and transient camera, but they're very inefficient for time-gated camera rendering. And let us see why. Further, here is an illustration on like why it's inefficient for time-gated cameras. So most existing path sampling techniques, they have no control over the path length, right? So they generate paths agnostic to the path length. And most of these paths that are generated, right, are going to be weighed with some weight, but they're accepted by the continuous wave time of flight camera and the transient camera. Whereas time-gated camera, most of these paths are going to get rejected. Only like 1 or 0.1% of the paths are going to get accepted by the time-gated camera, meaning most of the paths that we have generated are going to waste. They're getting multiplied by just 0, right? So it's a lot of wasteful path generation, and hence rendering for time-gated cameras is difficult. So I'm next going to show about a path sampling technique that we developed to overcome this problem. Before that, are there any questions? Yes, Praneeth.
A very basic question.
Yes.
You're shooting rays from the source and you measure it with a intensity camera.
Right.
And if these are randomly, like if these rays are randomly shot, there's no guarantee that all the rays are going to land in the camera.
Right.
So if you generate 100 rays, maybe there's 2 rays that are.
Yeah, so there is small tricks that are done there. For example, in the path tracing, where we start from the camera and we generate a random path. In the end, we do something called next event estimation, where we do a direct connection from the light source to the path end. That way, we guarantee that a path is created. Okay. And in same thing with light tracing, where you start from the light source. But in bidirectional path tracing, what we do is we start from both the ends and we join those paths to get a path. But in all these techniques, there is no control over the path length. That was the biggest problem. Why time-gated rendering is a huge challenge. Any other questions? Awesome. So, so what we did, like I said, we built a procedure that is optimal for time-gated rendering. And basically what we did was we started like this. We said, okay, the time-gated camera is going to have a narrow path length acceptance range. So I'm first going to sample the path length. So I'm going to sample the path length. And this guarantees that the path that is generated with this path length will always get accepted. So the next task I need to do is generate a path that has this fixed path length. That's all, right? So the starting point for my step 2 is the bidirectional path tracing that we were discussing. So we generate a light subpath starting from the light source, and then we generate a camera subpath starting from the camera and tracing a random walk, doing a random walk and tracing a random path. And the traditional one, we join the source subpath and the camera subpath end, and that's the reason we had no control over the path length. So what we proposed was, instead of joining them directly, we'll join them via a connecting vertex, so that the position of this vertex give me this additional control to control the path length, right? So in particular, what I need to do is I need to generate this vertex so that the total path length, which is the sum of the green arrows, the blue arrows, and the yellow dashed line, or the sum of the source subpath length, the sensor subpath length, and the new 2 edges that were created because of the connecting vertex, the total path length is constant. Or in other words, the sum of the yellow dashed lines is constant, which is the definition of an ellipsoid, right? So from a point, the sum of lengths to two unique points has to be a constant, and that's the definition of an ellipsoid, which means this connecting vertex must be on an ellipsoid, right? And so now all I have to do is intersect this ellipsoid with the scene, and that's it, done. I get this vertices which give me the exact path length constraint. Okay. And based on the location of this ellipsoid, we have two main scenarios. If the ellipsoid is inside a scattering medium, then it's easy. You can sample any point on this ellipsoid, and that's a valid point, which is both on the ellipsoid and on the scene. However, if the ellipsoid is on intersecting surfaces, then we need to determine these points and then randomly sample one of the points on these intersection points to create this path. Sounds good? So this is how we built efficient rendering technique for time-gated cameras. So accurately simulating time-gated, yes.
And someone asked in the chat, in practice, what is this kind of multipath effect for time of flight camera? This is a question by James Young.
Yeah, thank you, James, for the question. We will see some, there are both good effects and bad effects of multipath, where the question is basically, if you have multipath effects, is it good or bad to time of flight cameras? It's actually good and bad simultaneously. For continuous wave time of flight cameras, multiple paths actually corrupts the phase measurements, because of which we get inaccurate depth measurements. Most of the times, time of flight cameras are used for depth measurement, and it kind of corrupts the depth measurements because of multipath. There is also a good side to that. Light that bounced multiple times carries information about the regions that are not directly visible. So around the corner, I cannot see the people, but light from them is bouncing and coming to me, and that's called as the non-line of sight imaging problem. And we are actually going to see next after this part on how we can use time of flight cameras to look around the corners beyond line of sight. Okay, yeah.
But it's like for you to be able to just sample on the ellipsoid or any of the things that you mentioned, you're assuming all the surface completely numbered.
They can be specular, but if they are purely specular, like for example, if they are like mirror-like, then it's actually is going to have a path contribution which is very, very low. But that actually, sorry, I'll get back to you. But there is actually, like, how do you, among these points, how do you import and sample is actually an open problem that's still under something that can be investigated. Yeah. Sorry, sir, your question?
But you need multiple points of time to generate multiple points for the samples of different time. So you generate random rays and then have a set and pick the one for the particular time point that you need.
Okay, sorry, I did not get the question, but if you don't mind, can you speak on the mic? Yeah, thank you.
Yeah. So we have a case where you need to find a ray of particular length to match that time point, right? But you will need multiple time points for the full simulation.
If I want to do full simulation, yes.
So why not just generate a whole bunch of rays, keep them all, and then select the ones for the particular time points that sort of roughly match, you know, as the correct length for that point in time.
Okay, so if the I think there are two parts to the question. Correct me if I'm wrong. So you're saying you are interested in multiple time samples. So why not keep the path, keep the source path and sensor's path, sample the time multiple times and get multiple ellipsoids and do the intersection? Is that what?
Just completely avoid the ellipsoid. Generate, so knowing that you're going to generate a whole bunch of time points, you need to simulate them all.
Right.
Generate all the rays that you need beforehand. And
right.
Then you have rays to select from that have the right length for that particular point in time that you're interested in.
Right. That sounds like there is an algorithm called photon mapping, which is similar to what you said. The problem there is these narrow path lengths are the path lengths of the time-gated cameras are really narrow, like 1% or 0.1% of the total scene, which means you're almost sampling on a delta manifold, right? So you need to have you need to sample two paths, and you should be lucky enough that they have the same exact, so that the total path length is exactly equal to the path length that you're trying to sample. Okay. Does that answer your question? I'm sorry.
I think what you're saying is that the chance that you find rays that are of the right length for a particular point in time, you generate a whole bunch of.
Right, it's still low. It's going to be low. Yeah.
Yeah.
So there are people who did this kernel density techniques where they weighed, saying that, oh, okay, they are not exactly the same path length, but I will give some kind of a Gaussian weight, saying that, you know, far away ones, maybe the intensity contribution is equal, things like that. It's called photon mapping techniques. They do work, but they give what is known as bias, which is hated in scientific imaging community. Yeah, thank you for the questions. I like this interactive talk. Awesome. So we saw how we can build the time-gated rendering. Next, let us look at some applications of time-gated rendering. And like I was saying, there are companies like Brightwave Vision, which makes this time-gated cameras. And one of the applications can be like a proximity detection, where you're only looking at so basically you're kind of creating a virtual light curtain by imaging only light coming from a particular time range. Okay. So if there is any object within that's having this particular time range, then I know that there is an object that's coming to hit me or very close to me. So we can use them as a proximity camera. What happens if I simulate a road scene where we are doing this proximity detection with standard BDPT and the BDPT with ellipsoidal connections? This is how the renderings look like. It's very difficult to see the difference in the video, so I'm going to show a couple of frames. Right, and here you can see that the standard BDPT versus the BDPT with ellipsoidal connections for the same amount of time, rendering time, you can notice that our technique was significantly better than the previous technique. Okay, sounds good. We open source this time of flight renderer. It's on internet if any one of you wants to play with it. And after we made it open source, it was used for multiple applications, including non-line of sight imaging, depth sensing, tissue imaging, sensor design. People who were building time of flight sensors, they used our simulator. Obviously, deep learning, you want to generate a lot of data. With these non-conventional sensors, generating huge amount of data sets is hard. So you can use the simulators to generate large amount of data sets. People use it for inverse rendering and also for sonar, something that we did not anticipate before. Even though we built it for light, the sonar measurements also are time of flight measurements. So people also use it for sonar imaging. But what I'm going to do next is I'm going to talk about a non-line of sight imaging technique that we developed, known as temporal focusing. And we are going to see how renderer is going to help us in finding the optimal design parameters for this temporal focusing technique. Okay. So once again, with respect to the overall tutorial, so far we learned about how to do physics-based rendering and extend the formulation to time-of-flight cameras and build time-gated rendering techniques, which time-gated rendering techniques required new path sampling techniques. So we saw how we can come up with new path sampling techniques. And next, we will look at the non-line of sight imaging technique and how the rendering optimized design can help us build better hardware. So non-line of sight imaging refers to imaging objects around the corner beyond line of sight. In this specific case, we have a bunny around the corner, and both the light source and the camera are in a different room. And these both the light source and camera are separated from the bunny with the help of a wall, because of a wall. And there is no line of sight between both of them. We have a diffuse wall from which the light can bounce and reach the bunny. And that's the only source of information for us. And if this wall happens to be a mirror, then it's a trivial case. We can look around the corner. There is nothing great about it. But now we have a diffuse wall and we still want to look around the corner beyond line of sight. And we could think of several potential applications on non-line of sight imaging, cave exploration, medical applications, or to locate survivors who are caught up in some unfortunate situation. There is no line of sight between the firefighters and the survivors, or in autonomous cars where there might be a child around the corner in the blind spot of the car because of some other obstacles. These are all cases where you can use non-line of sight imaging techniques. And there are quite a few techniques to image around the corners that were developed by several researchers working in computational imaging field. I do see some of them here. So what I'm going to do is I'm not claiming that I'm going to show all the techniques, but I'm going to talk about the technique that we developed and that we have optimized with the help of renderer. And we are going to see that next. And our technique is motivated by line of sight imaging. Just like how we do line of sight imaging, we wanted to do non-line of sight imaging as well. Okay, so in line of sight imaging, to image an object, all we do is we use a lens. Lens takes light rays coming from the object of interest and focuses to a pixel on the camera. And we want to do something similar for non-line of sight imaging as well. So we have this non-line of sight imaging scene, and we need to see how we can focus the light coming from the bunny onto a pixel on the camera. That's what we want to do. Okay. And by the way, the detectors that we used for non-line of sight imaging, they were all single pixel detectors, which means they have only one pixel, they don't have an array. So what we are going to do is we are going to see how we can focus on a point voxel and then scan the hidden volume. So I'm going to show how we can focus on a voxel, and then we'll just scan that entire 3D volume to image around the corner. Does that make sense? Okay, so how can I focus on a voxel? This includes both focusing the light from the imaging source onto the voxel and also the light coming from the voxel onto the camera. That's what I want to do. And how can I do that? So what we are going to do is, because there is symmetry and there is also a guarantee from Helmholtz principle that if I solve one problem, which is how do I focus light coming from the voxel onto the camera, that problem kind of gets solved for us. It's going to be exactly the same. So I'm going to focus on that. How do I focus light coming from the voxel onto the camera? Okay. Well, it does look still hard. So what I'm going to do is I'm going to make it easy. I'm going to assume that the wall is a mirror. Now, how do I image if the wall is a mirror? Well, simple. We have a line of sight case, almost a line of sight case. So I'm going to use a lens. And if focused properly, the cone of light rays coming from the voxel of interest, they are going to focus onto my sensor pixel, right? And what I'm going to do is I'm going to separate the real rays from the virtual rays. The rays that we saw going inside the wall, they really don't exist. They are virtual rays, but the real rays are going to reflect. Okay. Now, instead of a mirror wall, if I have a diffuse wall, these rays still exist. And hence, I should be able to focus around the corner. But I cannot. I can look into the wall, stare at the wall for a very long time. I cannot look around the corners. Why? What is preventing us from looking around the corners? It's actually two major challenges. One, out of focus voxels. The other points which we are not interested to focus on, they also send light because of scattering, right? It's a diffuse wall. So because of scattering, they send light and it decreases the signal to background ratio, right? So we have a huge signal to background ratio problem because of out of focus voxels. But notice that the time of travel from the voxel that we are focusing to the out of focus voxels is going to be very different. So all I need to do is take a time gated camera and use an exact time gate so that light coming from the out of focus voxels is kind of removed and only in focus voxels is imaged. So using the time gated camera, I can boost my signal to background ratio. Okay. However, there is another challenge, which is non-specular photons. If the wall is mirror, all the photons are specular, meaning all the light gets just reflected off of the wall. But in this specific case, light gets scattered in all the directions, which means very little amount of light is actually coming to my camera. So I'm losing a lot of light. So I have a signal to noise ratio problem. So signal to background ratio problem, which we can solve with time gated camera. And we also have signal to noise ratio problem. So how do we solve this problem? Well, we can use a large lens, a huge lens, and then that gathers a lot more light. However, large lenses are expensive, bulky, and not practical. But really, what does a lens do? Well, lens delays the light rays such that they reach the detector at the same time instant. So all the light rays that are coming from the voxel or whatever point that we are trying to image, they go through this lens, okay? The ones which are traveling through the center of the lens, which have shorter geometric path length, they are going to travel through a thick glass slab. They are going to be delayed more. Whereas the light that goes to the periphery of the lens, it's going to get delayed less. And in the end, all the light rays which focus onto the camera, they are going to have exact same time of travel. That's the Fermat's principle also, right? So large lens is impractical, but can I imitate or mimic large lens? Okay, that's what we call temporal focusing, where we initially theorized saying that what if we built a delay array so that we delay the light in a specific manner so that all the light coming from the voxel that we are scanning right? It's going to come to the camera at the same exact time instant, but all other light will have different time instances. That's what we thought, but building this delay array turned out to be very expensive. So what we also noticed was, what if I only image light rays which have a constant delay on the wall, right? So if I image a specific ellipse on the wall, all the light rays are going to have the same exact time of travel. Okay, so that's what we did, basically image on an ellipse, and all the light rays coming from the in voxel are going to have the same exact time of travel, whereas out of focus voxel will have different times of travel. And on the illumination side, it's going to be symmetrical, right? Helmholtz principle, and you can once again illuminate on an ellipse and you are done. Yeah, do you have a question?
So if you do the time delay, you're basically going to sample all the light parts that have the same path length.
Right.
Yeah, if there was only one voxel, then sure, you sample few ways and that.
Right.
But if you have a volumetric scene,
Right.
Multiple parts would still, I mean, light from multiple points on the volumetric scene would still have,
Yes.
might still have the same path.
Might still have, that's the most important thing. So all the rays coming from the in voxel, in focus voxel, are going to have the same exact time of travel. All other things might have this thing, and that might have is actually important because they cause some background. So there is going to be still some background that is there, but then we are boosting the signal to background ratio a lot. It's a very excellent question, because that drives me to the next slide. It actually drives the question like, I have so many design parameters now. What should be the thickness of this ellipse? Because if I increase my thickness of the ellipse, in some sense, I'm getting more light from out of focus voxels, right? And should I use like large ellipses or small ellipses? And there are several time of flight cameras out there in the market. Which time of flight camera should I use for a specific design constraint that I have, right? All these are important questions that cannot be analytically analyzed. So we used the time-gated renderer that we have built in the previous section to optimize for the specific case. Does that make sense? Yeah. Any other questions? Yes, they will be available on the website. For some reason, our website is not showing up on the CVPR page. We saw that, but it's available on my website. If you type my name Aditya Pedredla on my website, there is a link to the page, and we'll put all the slides and recording there.
I think there is also a question on Loop by James Yankovic. Could this also be done with an event camera with a narrow band filter and a very bright brief light bulb?
It's a good question. Event cameras, the time resolution is still I believe it. The best one that I saw was giga events per second. The best event camera that I saw was giga events per second. I'm assuming that it can have a resolution of like a nanosecond. So the nanosecond resolution is actually pretty poor, which we will see in the next slides, that it might be hard to do non-line of sight imaging at meter scale using an event camera. Maybe at a very, very large scales, like in kilometers or tens of kilometers, maybe we can do with it, but then we need a powerful laser source in that case. So probably it is very hard to do it, but theoretically, yes. Yeah. Thank you, James, for the question. Any other questions? Awesome. Okay, before I show the effect of design parameters, I'm showing here a comparison of the standard BDPT technique to render temporal focusing with our renderer. You can see that standard BDPT technique cannot even render the hint of temporal focusing, whereas the efficient time-gated rendering technique that we built was able to render in a couple of hours the non-line of sight imaging sync. So we used that. And we studied various design choices, and we observed a few things. One thing we observed was, if we increase the ellipse size, the reconstruction results, or the image results, they improve significantly. This is similar to how you use a large lens, the diffraction blur decreases. It's the similar kind of an effect. Large lens gives you better resolution, and large ellipses also gives you better resolution. If we increase the thickness of the ellipse, or if we decrease the thickness of the ellipse or increase the temporal resolution of the camera, we notice that we get better results, but at the cost of losing light. So there is a SBR to SNR kind of a trade-off that happens in this case. So using these learnings and with these trade-offs in the mind, with the things that are available in the lab. Yeah, sorry, Pranil.
smaller ellipse means time gate is early.
Earlier, exactly.
So, is there an illusion on why time gate is later is
Right. It's better to think of it from the aperture point of view than the time gate point of view. So you're taking a larger aperture, and hence you are getting like better resolution.
In some sense, it's like you're only going to sample the chief rays.
You are sampling the chief rays. Why? No.
All the objects, only like if that was a large lens, you're sampling less of the rays that are sampling more rays that are
At the periphery, yes. So they will have more diversity in some sense that the background gets kind of decreased, if that makes sense. But since once again, since you're from optics background, I was using the same thing that if you have a large lens, you have, that's the reason we use DSLRs which have large lens compared to our phone cameras which have like a really small lens. It's something similar here. Yeah. We can discuss more after the talk. Yeah. So yeah, like I was saying, with these trade-offs in the mind, we built a hardware prototype using SPAD detectors and picosecond laser. And to image and illuminate ellipses on the wall, we use like a high-speed galvo and time multiplexed to generate these ellipses. And based on the conditions we have in the lab and imaging requirements, basically we selected optimal parameters based on the renderer. And just to show you the impact of renderer, these are the results that we got when we used a previous design without using the renderer optimized design. And on the right are the results that we get if you used an optimized design. The results are significantly better. Now, theoretically, we could also compute these optimal parameters by changing various components of the optical system, because we built this hardware. So technically, you can replace one part with the other part and all. But there are so many choices for galvos or picosecond lasers or SPADs, like the detectors and so on. And if you think about all these permutations and combinations and the costs involved, also the human costs involved to do this experimentally, it would take like several years to do that. Whereas all I did was I threw it on a cluster, and in a week I knew what's the best parameters that I need to do for building my imaging system to be. Sounds good? Yes. Uh-huh.
So you post on the time the side of the ellipse,
Right.
but also it affects the distance of the also that you're looking at, right?
Not so it's actually so so think of this thing. So if I take a voxel and the camera point as locus, and I draw an ellipse of a particular time of flight, that's going to intersect at the wall with sizes of ellipses of different size. So if I take a larger ellipse, it just corresponds to light coming from the same voxel but a different time of flight, right? So larger ellipse just corresponds to light coming from the same voxel but at a different time of flight.
So how do you control the distance of the voxel if you want to look at?
It's a function of two things. One, the size of the ellipse that we are imaging, and the time gate. So if you increase the size of the ellipse and the time gate, you are getting light from the same voxel, right? If you change the time gate, then you are getting light from a different voxel. Yeah. Okay.
So basically, you put a large and you sweep through the time gate. So that would be the best resolution reconstruct in the wall.
So if I fix the ellipse and sweep on the time gate, you said, right? If I fix the ellipse and sweep on the time gate, I'm scanning different voxel each time.
Yeah, so that way so a larger ellipse is going to give you a better resolution. When you see that will give you probably the best resolution volumetric reconstruction.
If I sweep on the time, no. If I want for the same voxel, if I want more light, what I had to do was for that, we actually used a time gated camera, fixed time gate, and then we use different ellipses. That's how we implemented it. Yeah. Yeah. So we'll proceed on and then circle back to these questions. Yeah. So like I was saying, yeah, this would cost us a lot of money and time that got saved by that. And next, let's look at some hardware results obtained. The main advantage of temporal focusing is we are focusing all the illumination resources and imaging resources to a small volume of interest. So if we scan the full volume, the previous techniques and our technique, there is actually no additional advantage that you get. But if you are scanning a specific region of interest, then our technique actually gives a much significantly better result compared to the previous techniques. And we experimentally observed a 10x higher signal to noise ratio when we focus to a small region. So this could be like a hidden or a hidden corner or something where we might expect some kid or somebody to be there. Most dangerous place that's where we can actually keep looking at using our technique. And just to demonstrate that experimentally, what we did was we kept a metronome around the corner, which was oscillating, and we always focused on a specific voxel. And you can notice this is the transient that was measured, and this is the time gate that we are taking. And we notice that we can detect the metronome's position at around 10 frames per second. Okay, sounds good. Okay, I think I'm doing slightly bad on time, but I'm happy with the questions. So please keep asking the questions. Before I move on to the next topic, are there any questions? Any further questions? Okay, so with respect to the overall tutorial, so far we have learned how to do physics-based rendering, how we can extend it to time-of-flight cameras, and how we can develop new path sampling techniques for time-gated cameras, and how it is useful for non-line of sight imaging. Okay, now we are going to see a specific physics between how light and matter interacts in continuous refraction and scattering that is used in acousto-optics that was previously ignored by rendering techniques or computer graphics, but how handling that gives us more power and more control and more optimization capabilities to optimize new imaging systems. That's what we are going to do see next. For that, what I'm going to show is I'm going to show some motivation with a photothermal therapy application. It's a cancer treatment where the goal is to heat up the tumor with the help of light. So I want to focus light onto this tumor, heat it up, and kill it. For that, one thing I can do is I can use a lens, right? And if there is no scattering tissue, right? And if I send light, the light will refract once at the boundaries of the surface of this lens, and it's going to focus onto the tumor. And it's going to heat it up and maybe kill it. But there is tissue which scatters light, which means most of the light that we actually try to focus scatters away from the tissue, from the tumor, and it's going to actually heat up the healthy cells and can also kill them. So focusing onto this tumor is very important. What we did in our lab is took another approach of focusing light onto the tumor by using ultrasound. Okay, so we used an ultrasound which creates ultrasound waves which modulate the tissue. So sound is a pressure wave which, while it is traveling, it compresses the medium and rarefies the medium as it propagates, right? So it's compressing the density of the medium, and the refractive index of the medium slightly increases, and during rarefaction the refractive index actually decreases. So we use ultrasonic array to create stationary pattern and convert this tissue, the scattering tissue, into a lens, into a waveguide or a lens, right? So once again, this would be, for those of you who are familiar with green waveguides, this profile that we created was similar to a green waveguide. And once again, if there is no scattering tissue, if I send light now doesn't just refract once, it continuously refracts because the refractive index is continuously changing. So it continuously refracts and travels in curved light paths before it focuses onto the tumor and heats up this tumor, right? Now, if I have a scattering tissue, light still scatters, but this refractive index profile that we created has this property that it guides even the scattered light back onto the tumor. Okay, make sense? Now, when I first saw this technique, I felt it was unbelievable that I can sense sound and somehow convert the medium into a lens. So I know most of you might also be feeling the same way. So what I'm going to do is I'm going to jump ahead and show an experimental result that we captured to show that it's actually possible to convert a medium, even a scattering medium, including a tissue, into a refractive waveguide, gradient refractive index waveguide. Okay, so here I'm showing the typical setup for guiding light through a scattering medium, how the setup looks like. In our lab, we have an ultrasonic transducer here, and this is how the setup looks like when we have scattering medium. We won't be able to see the transducer, and that's the reason I showed the image with when the medium was water, but in general, the medium was a scattering medium. And we have a fluorescent target that looks like a CMU here. And when we send light with ultrasound off, the light gets scattered and this is how the scattered beam looks like. And when I turn on the ultrasound, the medium gets converted into a lens, and we are seeing the CMU target on the camera. Does it make sense? Okay. Unfortunately, we have a high dimensional problem here because there are several parameters that we can tune here. We can tune the ultrasound frequency, voltage, the placement of transducers, the shape of the waveguide, and the waveform that we can drive the ultrasound transducers with, and so many other parameters. So how can I do an optimal design when I had so many parameters? Well, the approach that we took in the last two chapters, the same approach we are going to take here. What we are going to do is we are going to explore with the help of rendering. And for that, we need to build the very first renderer that handles both, very first rendering algorithm that handles both continuous refraction and scattering effects. Does that make sense? Setting of the problem? Okay. So to simulate virtual waveguides, we need to simulate two complex light matter interactions or light transport effects, namely the continuous refraction, where the light continuously curves because the refractive index is continuously changing, and light scattering, where light's direction randomly changes because of the scattering particles inside the medium. And both these effects were independently studied both in graphics and physics, and there are many, many papers that were published on them. But when put together, continuous refraction and scattering, there's not even a single unbiased physics-based rendering that was available. So what we did was we built that algorithm for so that we can do analysis of the scientific imaging system, the acoustic imaging system. Okay, so let's see that next. So for that, let's understand what is meant by continuous refraction and see how we can handle it. Even before that, let's assume that there are only two refractive indices in the medium. Okay, so there is one refractive interface. So the refractive index is changing only at a single plane. Okay, so here, if I'm trying to do light tracing, because of refraction, the light ray will bend once at the interface of these two media. And we know from the high school, this is handled using Snell's law. So this Snell's law will give you the direction of the light ray once the light refracts. And if the number of interfaces increases, the number of times the light ray bends also increases. And by continuous refraction, these are basically media where the refractive index changes continuously, and hence the ray continuously refracts. Okay, and we can trace this light ray using what is known as refractive ray tracing equations. And along with continuous refraction, if we have scattering particles, the light ray is also going to scatter. So a typical light path is going to look something like this. Light ray is going to continuously refract, scatter, continuously refract, and so on. And if I have a camera here, like Pranit said earlier, most of these light rays will not even reach the camera, right? So how do I build path tracers, which can how can I find a path which starts from the light source and ends at the camera? For that, we are going to start with the path tracing techniques that were developed for constant refractive index media and see how we can extend them to continuous refractive media. Okay, so for constant refractive media, radiative transfer equation is the one that models how the light light gets transported through the medium. Okay, so and we have seen that we can use bidirectional path tracing to trace the light paths, and let's see if we can use the same technique here also. Okay, so for that, I started with the light source, traced a random emitter subpath, right? That's what we can see there. And we started with the sensor and traced a random sensor subpath. And next, what we need to do is join these two vertices with a straight line. Unfortunately, light doesn't travel in straight line in this medium, which means if I join with a straight line, that's going to be an invalid light path. That's not going to be an accurate light path. So we need to find a curve that satisfies refractive ray tracing equations like the Snell's law at each point on that curve. That's what we need to find, right? So what we did for that is, if I know the starting point and the direction, then I know how to trace the path, right? That's what we were doing so far. Using the refractive ray tracing equations, I can trace this path. Okay, so we started with some random initialization and found some path. And we defined error as the distance between x3 to this path. And by minimizing this error, we computed the path which starts from the sensor subpath and joins the emitter subpath end. Does it make sense? Okay, this is at a high level. However, if you are interested in like how does light travel through this continuous refractive media, how we can trace it using Hamilton equations, or how can we differentiate it and do that analytically so that we can do it really fast. Those techniques are those details are available in our paper that you can find online if you're interested in, or you can use our simulator that we gave available online and directly use it and forget about all this math too. Yes, sir, you have. Yes. Can you please talk on the mic if it's okay? Yeah, thank you.
If the curve has based on something like this, actually,
Oh, least path length principle, Fermat's principle, right? Yes, it's in some sense we are trying to find a Fermat path. Yeah, this is going to be either the maximal or minimal path length. So yeah, it's a not shortest path, but a stationary path. That's what we are trying to find. Yeah. Any other questions? Awesome. So let's see. Yeah, right.
So that going to always be constant in the sense when you are facing these parts, you know exactly what.
Yeah, we know the refractive index profile. Yes, and I think Yanis will talk what if we don't know and what if we want to design those refractive index fields. It's also possible actually. If you want the light to go in a specific way, what's RAF? That's also computable today. Yeah. Any other questions? Awesome. So even though we built the render for acoustic waveguides, the technique is generic and we could use it to simulate arbitrary refractive index and scattering cases. And we considered this example of Lüneburg lenses. These are special kind of lenses which have a refractive index profile which decreases radially. And standard Lüneburg lenses has this property that if parallel beam of light rays come, they will exactly focus on the surface of the Lüneburg lenses. So these lenses have like very high field of view, and people expect them to be used in applications, autonomous applications, and they are being developed further. And by playing with the refractive index profile, we can actually control the focusing power of these Lüneburg lenses as well. So what I did was I took these Lüneburg lenses and I kept it inside a Cornell box scene with different power and just tried to see what happens. And here we can see the volumetric focusing behavior of various Lüneburg lenses. So I also filled this room with a fog. That's the reason you are actually able to see where the intensity of light is highest and lowest. So what I'm doing here is, as I went from left to right, I actually increased the power of the lenses, and you can see that they keep focusing and then they start defocusing and all. But one cool thing that I noticed was these Lüneburg lenses don't have standard Gaussian blur kind of a shape, but they have like a donut kind of a blur shape. That's kind of interesting. I showed time of flight rendering earlier, and we could do the same for continuous refractive media also. One catch here is the time of travel needs to account to the fact that refractive index is changing, and hence the speed of light is also continuously changing as the path is being traced. That's one thing that we kind of need to handle. And we can see the beautiful transients that are going through continuous refractive index media and constant refractive index media. A lot of things are happening. So I'm going to freeze a couple of frames. This is the first frame that I'm going to freeze. And you can notice that for constant refractive index media, in some sense, the transient is traveling faster compared to continuously varying refractive index media. And the reason that happens is because you need to use multiple glasses and fuse them to create that media. And hence the net refractive index is actually slightly higher than a constant refractive index one that we use. Another interesting thing that we can notice is the red light is coming before the blue light. It's exiting before. Here also you can see the blue light coming, right? And if I freeze one more frame here, you could notice the rainbow colors, the light is getting split based on the spectrum as it travels. And the blue light is coming late compared to the red light. In both these cases, we can notice that. This happens because for glasses and most materials, the refractive index is a function of wavelength. And for blue wavelength, the refractive index is higher, because of which the blue wavelength is actually traveling slower. So this render, even though we built it for scientific applications, we can also use it to explore physics and kind of understand physics by just playing with the render. Anyway, we built the render for optimizing virtual waveguides. So we need to see that. Like I said, we have several parameters, and we need to optimize, play with all these parameters. So we did that, and even before we see those results, what I'm going to show is I'm going to show the real measurement captured with our hardware versus the bidirectional path tracing technique, our technique that we built, versus the previous photon mapping techniques that people have built. I hope people can see the difference clearly, at least on my screen, it's clear, and hopefully it's also clear on that screen. The technique that we have developed, the data is much more closer to the real data compared to the previous photon mapping techniques for the same amount of rendering time. In a more controlled case, we compare the experimental data with the render data for two operating regimes of the acoustic optics as shown in these two rows. I'm also showing the 1D profile. By the way, everything was shown in logarithmic scale, so I'm actually exaggerating the differences, and still you can see that both the experimental data and the render data looks very similar, except for these ringing artifacts that we see in the experimental data, which is a wave phenomena, wave effect, which we did not model in this specific rendering algorithm. That's the only difference that we can see in both these cases. In the interest of time, what I'm going to do is I'm going to jump ahead and show the final result. So we optimized the acoustic optics and studied with it. It's also accepted as a paper. But what we did was we optimized these waveguides, and we showed both computationally and experimentally that compared to an external lens, an ultrasound focused lens is actually 3 orders, like 50% better than the external lens. And our designs that we have optimized with the renderer were 4x better than the previous designs that people have come up with. In this specific case, you can see that even if I zoom in, external lens was not able to focus light at this depth, whereas the ultrasound optimized data, we were able to focus deep inside the scattering media. This could mean that we can cure tumors with the help of ultrasound focus light in the future. Okay, so far we have seen how stationary sound waves we can use, and we can convert the medium into a lens. Next, we will see how we can use traveling waveguides to build scanners, which are like 1,000 times faster than the scanners that are available out there in the market. But before that, are there any questions? Yes.
Another question. Until now, to my understanding, it looks like it's more like geometry optics, like
geometric optics. Yes, exactly.
this kind of techniques to with optics.
Right. It's an excellent question. Yeah. So with respect to wave optics tracing, something that Yanis is going to talk in the second half of the lecture, some of the wave effects we can actually render today. Not all of them, but many. The most important thing was the second order statistics. And Yanis is going to say how we can actually render it with physically based rendering techniques. Yeah. Any other questions? So yeah, so this is the last segment of before we take a break. And what we did here, like we built a scanner which is 1,000 times faster than light scanners using acousto optics. Okay, light scanning is a technique that is used in many projectors, microscopes, and also lidars, where we scan the light with the help of moving mirrors. Okay. What we did was we used acousto optics to make we used acousto optics to make the light scanning 1,000 times faster, and we achieved this by putting together the physics of how light and sound interact with matter, and ultra fast optics, fast synchronization electronics, and signal processing techniques. And let's see how this technique works. It's basically an extension of the acousto optic technique that we have seen so far. So far, we have seen stationary waves. What we did was we used traveling waves. That's the main idea in the next one. So For simplicity, what I'm going to do is I'm going to start with 2D visualizations. Our prototype basically consists of a compressible medium like water. And if I send light through this compressible medium, it just travels straight. Maybe it will refract once, but that's all, right? What we did was we placed a transducer. It's a piece of planar transducer that we kept in the water. And we drove this transducer with a sinusoidal voltage, which makes this transducer vibrate in nanometer scale. That creates these ultrasonic waves in the water. And like I said earlier, sound waves, when they travel, they compress the medium and rarefy the medium as they propagate. And compression increases the medium density and the refractive index of the medium, converting this medium into a set of lenses in this case, right? So if I send light now, light is going to continuously refract and focus at these points, okay? But light is traveling here, which means the focused points are also traveling at the speed of sound, which is 1.5 kilometers per second in water, 5 times the max speed. Okay, so we have a technique which helps us move the focus points at an incredibly high speed. However, we don't have any control over where we can illuminate, right? So for that, what we did was we used a pulsed laser and we synchronized the laser pulses with the ultrasound frequency so that we always illuminate the light source when we want to focus it at a specific location, right? That's when we turn it on, otherwise we don't turn it on. That's what we did. And we can extend it to scan multiple points also, right? Make sense? Okay. So far we have seen it in 2D. In 3D, if I use a planar transducer, we are going to focus on a line, not on a point. So what we did was we basically stacked 2 transducers orthogonal to each other. This way, the light started focusing at multiple dots. And one more thing that we did was we limited the illumination to only approximately one lobe of this sinusoidal lobe. Okay, so that we only get 1 dot focus. And by controlling the phase of both these transducers, we can actually come up with several scanning techniques, which allows us to scan this dot arbitrarily, or it helps us to scan in a rasterized manner, and so on. And these details are actually available on my paper that got published in this CVPR. This is the main idea. So we built the prototype. And we built the prototype with like a laser here. SPAD is a LiDAR detector. Both of them are co-located with the help of a beam splitter. And this is how our beam steering technique looks like. It's a bunch of transducers that are there inside water. That's all. And this will help us steer this beam. Okay. We also added a galvanic mirror so that we can have a one-to-one comparison between both these techniques. Okay. Yes, sir. We do. So that's the reason what we did was we placed this transducers at 45-degree angle so that the reflections actually don't come back to the main beam and they just die off. I also found out later after this prototype was built that we can actually also put acoustic absorbers on the other side so that they absorb this acoustic beam either actively or passively and kill off this beam and no other reflections come back. But yeah. Yes.
If you actually don't want the wave traveling, you also try to use a standing wave, right?
Right. Yeah, so we used a standing wave in the previous project. The problem with that is the standing wave, if it's not traveling, then I cannot steer the light, right?
You want that.
I want that to travel. I want that to travel as fast as possible so that I can steer as fast as possible. Yeah. Any other questions? Amazing questions, by the way. Oh, in this specific case, the tank was huge, and I didn't bother because it's a prototype that we were building. But yeah, making it small and compact is a future work. There's another reason that I did, experimental reason, was I wanted the ultrasound energy to dissipate without using an acoustic absorber, which I had to again engineer and all, right? If I have a large tank, it acts like a heat sink. Without keeping a real heat sink, it acted like a heat sink because I have a huge tank. But this tank is like, this distance is 1 inch. So you can see that it's several inches in size. In reality, we just need like a small size, like 1 inch or something should be enough. In reality, if we make it a production grade hardware. Okay. Any other questions? Yes, sir.
Still using standing wave like you did in this one. But if not using standing wave, then you cannot control the speed in which the wave moves, and that's why you need to use something that is
Yeah, exactly. I can, if I just want to scan it really fast, that's fine. But I also want to control the position, because, for example, if I'm doing a dot projector, I want to control where it is, right? Yeah.
So you can't control the speed in which it moves.
Yeah, I cannot control the speed. So standing wave, there is no speed. The speed is 0. But traveling wave, it's the speed of sound in the medium. That's all. Yeah. Any other questions? Yes, sir.
I was wondering, so I think pretty much all of the various applications that you showed and various techniques depend also on modeling like shapes and the physical characteristics of whatever medium you're using.
Right.
So I was wondering, like, mechanical precision, how important is it when you actually build the system? So I was thinking about this for the tumor application. So it's skin, they're not really.
Yeah.
Okay.
It's a good question because it leads to my next slide, where I'm comparing the rendering results to the hardware results. And you can see that the sizes of the A's are really very close, actually. So it's not that sensitive, not sensitive like third decimal and all. And in fact, I didn't even measure the refractive index of water. I just assumed it is 1.33. I got like very comparable results. So not that sensitive, fortunately. Yeah, so I compared with the rendering and hardware, and basically we used rendering to develop all these scanning techniques on software first. And once we are happy, we went to the lab and we built the prototype with the best optimal parameters. Okay. However, the remaining results that I'm going to show are all on hardware. They're not rendering results next. So what we did to compare our technique with the galvanic mirrors, which are 2 mirrors, right? Is we projected a series of dots that make this letter A, 100 dots that make this letter A. And I did this projection both with galvanic mirrors and also our light steering technique. And because our technique works at like a megahertz, it projects like a million dots per second. So in a millisecond, it projected this letter A 10 times over. It drew this letter A 10 times over. Whereas the galvos that are available out there in the market off the shelf, they were actually able to project literally 1 dot in that time. Okay. And even if I increase the exposure duration of my camera to 50 milliseconds, the galvo is projecting like 50 dots. And by the time the technique that we built, it was able to project this letter A, I think like 50,000 times. Okay, 50,000 divided by 100, 500 times basically. Make sense? So in the second experiment, we used a scanner in a LiDAR prototype, like the ones that we see in autonomous cars, which scan both the light source and detector. And we scanned like 100 by 100 points at 5,000 frames per second. In other words, we were able to scan 50 million points per second using our technique. Compare this with the VLS 128 prototype. That's the best LiDAR available out there in the market. With 100 lasers, it can scan 500,000 points per second, whereas we were able to do 50 million points per second, or 100 times faster with respect to scanning speed alone compared to the commercial LiDAR. Of course, there are other problems with our technique, which we will see next. But with respect to speed, this technique is like 100 times faster than even the Velodyne LiDAR. In addition to raster scanning the entire scene, our technique is so fast that we can do adaptive scanning. So, which means like if I scan with LiDAR and some region, the results are not good, I can actually go only to that region really fast and scan really fast. And our scanning technique can literally, from pulse to pulse, the first pulse fired by the laser, it can keep it at one particular location that you want. The second pulse fired by the laser, it can put it at a different location that you want. It can scan at that fast rate. In fact, we were limited not by the scanning technique in all our results. We were actually limited by how fast we can turn on and turn off our lasers. The laser became the new limiting factor in our technique. So in the specific case, what I did was I took 3 points and I scanned these 3 points adaptively using both Galvo and our technique. So Galvo was scanning the first point, very slowly it's going to the next point, and very slowly it's going to the next point. And in between, it is losing a lot of light to unnecessary regions. Whereas our technique, it scans the first point before the second pulse of the laser gets fired, it goes to the second point, scans it. That fast it scans. Because of this high speed, we got like 15 times higher depth accuracy compared to the Galvos. Like I said, there are some limitations not related to the speed because it's a new and completely radically different experimental prototype that we built. There are a couple of limitations that it still has. The first one is the diffraction limit. Since we are using two orthogonal transducers, we have an aperture that looks like a square shape. And hence, the blur that it causes will look like the product of two orthogonal sync waves, a sync sequence. In our phones, DSLRs, we know how the aperture is always circular, either with using by multiple elements of the aperture, we actually always make it circular, right? So in the future, what we plan to do is use not just two transducers, but multiple transducers cleverly synced and placed on a half circle so that we can get like an aperture which looks more circular and solve this problem. The second problem is I did everything in water because it's easy to keep the transducer smooth and all. However, water is not the best medium. The speed of sound in water is just 1.5 kilometers per second. But if you go to solids, the speed of sound increases much more. And the aperture, all of those things actually will improve significantly. So the next prototype, we are planning to either use tellurium dioxide glass or use some thermoplastics, which we can cure in the lab to basically suspend these transducers inside this plastic where the speed of sound is high, and also it's a solid prototype, which means we can actually keep it on autonomous cars without this problem that the water might spill or something like that. That's the next steps that we are planning to do for this specific project. Okay, so far we have seen any questions on this topic? Yes, Praneeth. Right. Yeah, there is a limit on the angular range, but we can always use an external lens to actually increase it. Just like the way the projector is there, there is a lens to increase the range. We can actually increase the range. So in this specific case, we did not do that. I think probably it will be a few degrees currently. A few degrees, couple of degrees currently. Yeah. But if you use a lens, basically you can actually increase that arbitrarily. At the, I mean, the diffraction limit will still show up, but you can actually increase it.
The second one, you said there is a traveling wave from the speed. Like, is it possible that you create a standing wave and then you move the standing wave?
Oh, create a standing wave, slowly change the standing wave over time. Interesting. But every time you need to refresh, right? So the standing wave to get generated, it takes the distance divided by the distance between the transducers divided by the length of the medium. The distance divided by the speed of sound. That's the amount of time you need for refreshing it. I think that would be significant. It won't be megahertz anymore. Yeah. You can change it, but the resulting device would be in kilohertz again. It will decrease heavily because of that. Right now, from wave to wave, from pulse to pulse, I'm able to tune it. Which is not possible if I do what you suggested. But it's a cool idea. Maybe for slow applications, maybe it's a good one. Yeah.
One last question.
Yes.
So right now the transducers, so I guess you're using a pulse laser. So
yes.
If you use a continuous laser.
Okay.
And have this transducer like this scan.
Right.
What is going to happen?
Yeah, it will continuously create that pattern, right? Which means either your camera should be fast enough to separate them, but today at least the ones that we have, we couldn't do that. We're limited by that.
By the time you change the what is the phase of the transducer, you want to synchronize the pulse.
Yeah, that's the technique we did because we are using pulse laser. But if it is continuous laser, as the wave is traveling, the beam is moving. So you don't have any control on it anymore. Yeah.
So I mean, like, this is essentially to make sure that you're scanning in a pixel or one scan.
Exactly. Yeah. Exactly. Yeah. Thank you for the question. Any other questions before we take break? Yeah. So just to summarize what we learned so far, we saw how to simulate exotic modern sensors and previously ignored physics of light matter interaction and how we can build amazing imaging systems to look around the corners or to scan the light at an incredibly high speed or to focus light deep inside the scattering. Yeah, that's what we have learned so far. In the second half, we will continue on this theme and learn how to render wave effects, such as speckle, or design tactile sensors that are used in robotics with physics-based rendering, but also learn about how we can differentiate all these forward models and hence build and build like differentiable rendering techniques where you can get the gradient with respect to any parameter and then use it in inverse rendering techniques to solve to solve basically inverse problems in computational imaging. That's what we are going to learn. But before that, let's take a 30-minute break and let's come back at 3:30. And Yanis is going to lead the second session. Thank you all for your time and attention.
Yes, sir. We're working for extreme. Oh, okay. Oh, okay. Yeah. So in fact, for UV, for extreme UV, in fact, the radiometric is approximately rate not much more the rendering technique that we can actually use. Not sure what full application for UV, yeah, we can use oh, the object is the width of oh, okay, I'm sorry. The object they like to show yes, there is a very important some
actually we are using now maximum
okay. So the next half, yeah, it's actually good to talk about how you can render speckles statistics during this and
so this up until now most of the objects are being images are allowed almost the lambda over 4.
Oh, depends on plan. Way more. But like I was saying, yeah, you can simulate. And I was going to say, so right now, we actually do that. So some example. In case you want to take
maybe because when we are dealing with such small object relation time actually
yeah,
we are anything so we are using now maxwell equations. Yeah, so 7 hours for frame of 1 micro.
So what I'm gonna show next is you can match exactly what it's called. And then scale the task match. That was exactly the problem. We're trying to simulate and we start with these finite element solver for actual equations or
Like IFCW,
yes, and there's another one we're using I mean there's one more that's trying to implement and a few of those, and they were all actually said that is my goal. Yes, like 2 waves, right? So we show that they can simulate certain they can simulate certain waves of it. I will not say that we still have full wave but already we have levels of simulation
this is for us, this is information which brings out our custom languages like TSMC. They are building objects which are like a building. 256. So the aspect ratio is 1 micrometer to 100 micrometers. And they ask us to put extreme UV on the top and give them the measurement for each and every flow. What is the width? So actually we image that.
I won't say it's a short term, I would say it's something we're working on. I'll push some stuff next and that kind of.
So it's not like silent element.
No, okay. But basically, we're trying to make everybody out. Because that's the key to more complex. This, I made it a very static, the blind person have an example, then the answer will show what. The whole point of this to avoid.
What time you are going?
Oh, nice. I think I saw your paper with Kiros. Trying to recollect.
Okay.
Oh, yeah, we have optical speed at CVPR.
Optical SPD. Ah, okay, yes, I remember that. Yeah.
And that means that.
Yeah, but that's the materials. So, currently, I am looking, let's say, not already filled. So we know that for your looking field is generally customers or your application model.
Right.
That's what they want. What you are wondering about some high order application model. You have or connection or something.
Global
Do you think that there is a good way to combine them together?
Yeah, we did think about that. I tried for a couple of
Noise less now.
things that didn't work out. And I also talked with the incident first one that I forgot his name. Yeah, incident NGP that he said he also tried, but did not give any different results. He gave exact same results. So he said, yeah, they also wasted some time and did not get anything. So at the end of the day, because we are using neural networks, the final results are the most important one. It seems first form is enough for now.
Yeah, good.
Yeah, congratulations on your job.
Oh,
Thanks so much. Yeah.
where are you going?
Yeah, I will start next year, April. I will start become assistant professor at Peking University.
Oh, nice.
Thanks, yeah, for
Yeah,
letting me
Peking.
Sorry, I didn't respond. That's a bit
You said
easy.
Peking, right? PKING.
Peking, you know Peking, the capital.
Chinese University.
Yeah,
Yeah, I know that. Peking University. I just wanted to be sure. That's all. Yeah. It's one of the.
yeah.
Is it the best or if not one of the best? One of the first two.
You know Peking Shi?
Boxing sheet?
Yes.
Yeah, watching.
Yeah, he's at Peking.
Oh.
He will be tenure this year.
So yeah, maybe the new plan. Let's say.
Yeah, I guess Peking is building it's hiring two Indian guys. One is me, one is Zoom. It's
How should Kate is.
yeah.
Like what is the name? You watch who did you have it? You watch yeah, Uzbek student.
No,
That's what you
How Shu was Katie's post. Maybe he was Beck's PhD. I don't know.
I see.
But his latest affiliation was at Caltech.
Right. Houston, right? Maybe SUN.
Yeah, and another PhD Abid is also
Abid.
yeah. So pretty.
Thanks, they hired David and then they hired and
I guess David is Abid is more about air science, black hole imaging. Well, David is
and also cloud tomography a lot.
imaging plus neural network, which is
No, Abiyad's speech was
Abhiyat's pitch was astronomy. I see. So his PhD work was on tomography, right? Cloud tomography.
yeah, but his speech was just
I didn't know that. Okay. But you there in his practice talks? Or?
I have information.
Yeah.
Yanis was most short person for criticizing talks.
basically we're talking about how to combine neural with this high order remote. I mean, so
multi-bonds and
I'm not gonna talk about that. I will talk about higher order differentials very briefly, and basically all of the applications which I will be for higher, they're not about how to rewriting the control.
I see. But basically, this is basically when we talk about image doing most of image is done by nerve.
I disagree. I mean, most of the networks are already different. But interestingly, is a much more broad. People use information across the science. Don't understand
I see. Yeah,
There's all the modeling problems and formal information. Now, we focus on novel use. But we, yeah, you can use single package. And the whole point is but that's not the only reason.
That's true. I guess.
In fact, differential rendering started from that kind of applications, from multi-balance applications, way before it existed.
on top of it.
Yeah, that's true. I guess that's one big problem. I mean, because I care more about the nerve, I work on the your nerve. So basically, nerve provide a good way to all easy to provide that means to the inverse problem, which you know that I want to mention here. To initialize it's like a very good relationship. You can just from scratch, which is the good point of your network. But the problem is that if you are trying to combine this nerve with this multiple like that.
But usually, it's not clear to me that for the kind of things that people do.
So, I mean, so at the beginning, so if you check the development of the nerve, so at the beginning, we only care about the primary, which is the camera origin surface. And then people start to adding more and more bounces from the.
But they really make it really different. There doesn't seem to be one for whereas most of the applications that we focus on are cases where you really need the multiple. So that's pretty much all of your secret.
I guess this is a very good question, but my answer is yes, because if you do not consider multi-bounces, it's very hard to separate shadows from the
Software doesn't require global information. Direct other the most important it will with them with just that's why it doesn't require changes. And just if you handle visibility is important, then you will get more. Now you will not get like the fact that and then but about in a photo in this style see that's going to be 2 pixels that have a slight the point is to get that kind of way.
Oh, yeah, same here.
With that don't okay.
I see.
So much more expensive than for that.
But maybe you can actually.
I actually thought that I'll find you the right field.
Which you do need to consider the glass transparency of that.
Well, this copy doesn't have that much of surface scattering. If you go and zoom in a bit, if you go and look at it like that, then yes, you will. So it's a matter of scale. It's really a matter of how important the process is to the kind of system.
I see.
And I would again argue that from the kind of view of room scale, or at least tabletop space, you can start global illumination is not good. But it's not important enough to be worth the ultra expensive multi-band training. Now, if we could make that a lot faster, I'm all for that. I don't know how we don't do that. But right now, to me, that's a big challenge.
I see. Actually, there are many. I guess there are several different directions on nerve. If we go a little high level, there is large scale extension. There is dynamics. There is. I guess that my is appearance decomposition, and also for some special material. They are people like to just because that we may not have verbal information. I get that more such concept require a lot.
I'll send you an email or something like that.
I still have to create an interpretation, but I'm not sure that's very gonna be installed by this. Thinking is
Yeah, so my point is that maybe you can combine nerve with multi-bounce revision, and then you don't need isolation, and you can also deal with some more special material.
I don't disagree. I mean, we also have the interest in the very complex materials. Again, that's how the started. Whether it's important in the context of nerve, given the kind of application and nerve cares about, I'm not sure. Definitely combinable, but it comes to have the big computational overhead.
Can I ask you? Well, this is not a very serious question, but I was just sitting there and I thought, what if you had a shock?
Interesting. I guess that's,
And now you have some really strong positive.
I guess I'm
And then you also have
imaging class,
right after.
which I
So
want
you
to
can sure this
know
continuity.
deeply combine all the different images.
This is just for fun type of
In types of LiDAR, like with spec, with reduced field, with this,
Yeah.
I guess that after that, 2 points in nerve. One is the neural repetition, which you can model a reduced field, or scalar field, whatever it's field. Maybe it's not just geometry appearance, maybe it's basically some physical. The aspect of the virtual imaging model, which gives you guys the percent will match the multi-bounces, image together to this inward problems. That's why I would say
But where do
For sure, for sure.
we know, but there's still language way to combine to make them very efficient, very stable. Yes, that's the problem. So we have to any you only have images which along this area, and you're going to try to extract everything
there are a lot of things
I see. Yeah.
So just the question I asked, just to make sure, how do you control markets
What's the main problem?
size of the ellipse and the distance? So there is, I'm just trying to correctly the parameter gating, meaning when
you should add more.
it's open, close, okay.
That's one parameter.
So what is the
So I'm imagining ellipse, meaning I'm only getting light from a particular, I can control the size of the ellipse.
but isn't that when you
Hack it, when it
goes before
If you fix that, like if you decided that, then the size of the ellipse is fixed.
Yeah.
So what we were doing was like, yeah, when I said I'm controlling the size of the ellipse, I'm actually controlling the time of light.
Okay, so how do you control? So this is, so you open and close to control the size of the ellipse.
Yeah.
But do you control the distance of the object? Also,
So based on the, I will try to write somewhere. Yeah.
Nice to meet you. Oh, nice. Kaushik was postdoc when I joined the PhD. He was very kind person. That's what I just.
Yeah.
I know Kaushik is amazing. How's he doing? How is his I know her daughter who was.
Trying to add some, make sure don't forget any. But go ahead, sorry, what you asked, so you were.
This is a boxes and scanner. So this is the difference of all the points of the light can scan. So that at the same time. That's where the ellipse. Ellipsoid.
And then I think
Whose focal points are fixed points. And this line is the time of hours. So because of my time of class, I fixed my ellipse. And but this voxel, the location of the voxel is fixed. The location of the voxel is already fixed. From that location, I got. If you want to say some other voxel, again, what is this ellipse? And then we get a different ellipse that is intersecting is first. And there is an ellipsoid and an ellipsoid. Yes. The ellipsoid intersecting the ellipsoid intersecting with the line is that ellipse. That's the same time of that fixes the size of the ellipse. Once you are given the voxel location, the camera location, and the time of flight, the size of the ellipse is fixed. Right? Then you need to different voxels which will have same types, not a lot of independence, but so there is something called focal cortex. Focal cortex is turns off for this ellipse that you have on the wall. If you draw a hyperbola, like the computer so if you take a voxel once the camera on one of these points and you have a particular time, you will get this ellipse. If you take this voxel on the hyperbola, has to be on the hyperbola, and the same camera, so the same ellipse. There will be exact focus kind of different times in the it is not that does happen. Yeah. So in some sense, by using one ellipse and taking the different ones, you are actually focusing on all the points. But on an oh, so we are using different time of light on the transit. Yeah, the normally the came out with this positive. It's very happy. So far, we patented it. We got the patent and it was much better than what we were anticipating. Thanks to the yeah, we patented it and we want to make it a much more solid. We currently don't have any commercial plans. Some company wants to buy us. Maybe even depends on us. And so much, but still moving. Yeah, that's amazing. But we still have challenges. Like two challenges are how do you make solid food? I think that is easy. How do you use multiple transducers? Synchronize this. How can you so that's
yeah, by the way, I'm not saying it's not gonna happen.
Yeah.
Oh, no.
Yeah, because it keeps giving us less kind of attraction there. And all of this, you might have seen some background there, and it moves better. Some background is actually coming because of the less. We can buy it. We can.
Yeah, we are convolving with that, so we can deconvolve. Yes, we can deconvolve. Well, we did not try something similar was tried for stationary ones by my system and you can actually check it. Both at same. They tried it and they got good results with that. But that's a post-processing technique. Post-processing is always post-processing. The imaging itself, I feel we can decrease it further. Yeah, it became a materials problem at a certain point of time. Like we wanted some of these materials. We are not material scientists, so we need to find some material scientists to help us with that. But yeah, the two problems that I mentioned can be solved. But commercializing it, I'm not sure. I'll be happy if some company goes to take it forward. My son Chamajar is the one who is more aggressively pursuing it. He is the one who actually first built the techniques. I saw the rendering opportunity and the rendering can help, but then realized that it's not under the exists, so we came up with our render and then we optimized it. So it's a bunch of different, but my son is aggressive. Hopefully he can take it further. That crossed my expertise at my level. That's the reason I feel I'm a secondary contributor in something, meaning I'm the one who's helping them. They are the ones aggressively pursuing it. Thank you so much. And it's just trying to force so you work with Felix. Yeah, I saw your papers from which I maybe we met last time and oh, maybe CVPR. Yeah, I mean, I'm going to say, yeah, enjoy. As you know, I'm part of even Singapore, I see CVPR at some other guys.
Hi. So, I'm going to use your laptop. Yeah, I got drop of technology, whether that's possible in your type of slide.
Oh, sorry, I didn't miss some questions. Sorry, I did not quite hear the next embedding material. Did you say rigid resin material or something more pliable like PDMS? I'll just answer James. Maybe he's not hearing me. So. James, we tried PDMS part in the UV resin.
Thanks. Anymore. That's me.
Oh, James. Ah, okay. Sorry, I just answered.
I was reading your questions correct.
Thanks.
Thank you for your questions. It's I think the second half is not showing up. It did not synchronize.
Maybe I should just show it from the.
Okay, but you need to log in again. Can you share?
Oh, but,
Yes, I will not close my laptop. I'll keep it on.
but why do we want that? How to record?
Yeah, because it's recording and I'm the host, I guess.
Okay.
Let me see if I can make you co-host. We have 5 minutes. I just
And slides. I added an extra slide before the authors. Actually, I made two changes. One is I added some collaborators. Can you pull up the closing slide? Because I want to make sure they actually.
I don't think it's synchronized because it's saying today at so and so time. Why
But
is
this
it-
did synchronize 320. This is now 320.
Oh, this is this. Oh, you
Okay.
changed this one and not
Yeah.
this one.
I changed both, but. Okay, so here I added one more slide. Oh, that's not the final version.
Okay, we have 4 minutes. Okay, you used yours. Yeah. Sounds good. Not yet. But you are going to use yours.
Yeah, but I don't know if I can do that.
Do you want me to plug in yours? Huh?
Give me a second. Oh, you have it.
I brought it from my desk. Just come back.
So you're gonna be monitoring patients now.
Yes.
Are you seeing my notes or are you seeing?
I'm seeing your notes. Yeah.
So, well, how come you were seeing the?
Did you stop share? Stop share. No, you need to play first. You need to do slideshow first. Then we need to go to Zoom, share screen, and screen door.
Okay. Can you go check that they are on seeing my, if there's no John.
So you can just
Yeah, but I'm worried about moving it because I may make it not at all safe. Yeah. All right, go ahead. So you're going to be monitoring the Zoom.
Yes.
Okay, so welcome back, everyone. I will continue with the second half of this tutorial. As in the first half, if you have questions, please interrupt me. You can either come to the mic or speak from where you are, or if you're attending remotely, you can post on Zoom, and Aditya will be keeping an eye out for questions so that he can relay them to me. So in the first half, we saw a few applications of physics-based rendering on time-of-flight imaging, on out-of-sight imaging, acousto-optics, and ultrafast lensing. We'll continue along with this pattern of applying different forward rendering techniques to different imaging problems, and we'll start with speckle imaging. Just a second. All right. So what is speckle? If you ever use the laser and you point it to any kind of surface that has some roughness, so basically anything that's not very, very, very smooth metal, you will see an image kind of like this. So there is this noise pattern, which has to do with the fact that you are using coherent illumination. The fact that you're not illuminating with an LED, but you're illuminating with laser light that, due to phase cancellations, produces this very high frequency random effect. So we call this speckle. And one thing you may notice that is this kind of image is completely different from what we normally render with Monte Carlo rendering techniques. So pretty much all of the algorithms are both I mentioned at the very start, the text to PBRT algorithm. The extension that Aditya has mentioned will never produce a speckle effect like that, right? Now you may be wondering, why do I care about this? This is noise, right? Why do I want to render noise? So it turns out that even though this speckle pattern is a noisy pattern, it actually has very strong statistical properties. It can give us a lot of information about the surface or the material that my laser light is interacting with. For example, it has a property called the memory effect that says that if I'm imaging speckle due to some scattering material or due to reflectance in some surface and so on, and I start moving around my laser, this the way the speckle will change will have a very, very, very strongly structured behavior. We'll see images that basically are correlated with each other with the extent of correlation preserving over some range of scanning. This is a property that sometimes goes by the name of memory effect. Like basically this speckle has some memory about the underlying conditions producing these random variations. And it has come up in the context of a lot of applications, a lot of imaging techniques lately in the context of tissue imaging. Basically, we can use this to try to image through relatively thin but still important and substantial layers of scatterers, which can be very, very, very thin tissue layers, or they can be other occluders that may be causing problems. For example, in the context of tissue imaging, this kind of memory effect has been recently used a lot for fluorescence microscopy applications. where the setting is as follows. I have some thin tissue layer that can be basically just maybe a millimeter or less than that of the very top of your skin. And I'm trying to observe fluorescent particles underneath that. These fluorescent particles may be something that I have injected into the bloodstream of a patient, and I'm using them to extract structural information about their vasculature. So if I use a microscope, and this is a lab prototype of this kind of fluorescent microscopy, I will see an image like this, basically an image that, because of all of the speculum, because of all of the scattering that has happened, as light propagates from inside the tissue through the tissue, doesn't give me any information whatsoever about what it is that I'm looking at. So the point of fluorescent microscopy is to try to find ways to descatter those images, to cancel out the multiple scattering and produce clear images of the kind of fluorescent particles that have produced this speckle effect over there. All right. And speckle can actually be a way among many different techniques that exist for this type of tissue imaging applications for doing this scattering effect. For example, there is this very simple and very effective technique by Ori Katz and his colleagues that they introduced in 2014 that says that because of the memory effect of speckle, it's very easy actually, again, within certain conditions and limitations, to descatter this image and get a clean view of the fluorescent particle that produces it. So here's how this works. If I look at the image that I capture without any scattering, it will look like this. If I look at an image that I capture with scattering, it will look like this. Even though these images both look very different, they have the following property, both of them. If I correlate them with each other, they will give me a result that is the same. So even though the images are very different, their autocorrelation is the same regardless of whether I have a lens-based system or a scattering that's transmitting the light to me. So with this observation, if I take the speckle image, form its autocorrelation, and then do a phase retrieval operation on this, I can go back and extract the clean image that we have observed if I was not observing through scattering, as I was observing using just a lens, using basically clean imaging, direct imaging. All right. This is a technique that Ori Katz introduced in 2014. It's drawn a lot of attention since then, but as I mentioned, it comes with a lot of limitations. For example, I want to make sure that within my image frame, I still have this memory effect property I mentioned. Effectively, I want to make sure the extent of the pattern that I'm imaging is within the range of changes in illumination such that speckle remains correlated. So I can go back to my fluorescent. Go ahead.
Previous slide, you said you do the autocorrelation, then do a phase retrieval on it.
Yeah.
So does that mean the image actually lies in the phase? What exactly is
the image here is intensity, right? So you can prove that the intensity image and the wave image, they would both have autocorrelation and is closely related to each other. So you can do the autocorrelation of that field, use that to estimate the autocorrelation of the wave you would have had, basically the coherent signal, and estimate the phase of that to get back the image you would have had if there were no scattering.
I see. So it's like you estimate the phase on the object plane or on the image?
On the image plane, on the image plane.
And then you go back up.
You don't need to do, I mean, in this case, we're not trying to do reconstruction. We're just trying to form an image, right? So if I have the phase and the amplitude of that component, I can reconstruct an image that should look like the one I would have had if I didn't have scattering. Okay. Yeah, for 3D reconstruction, I will need to do back projection, as you mentioned. Okay. So I could go back then into this fluorescent microscopy technique. And again, that's what Ori and follow-up papers have shown, and apply this technique, autocorrelation and phase retrieval, to get clean images. Now, of course, all of this comes with a lot of baggage. We can all image small scenes, and then things depend very strongly on the tissue parameters I'm imaging, on the settings of my sensor, on the different image priors I may be using for phase retrieval. Phase retrieval is a very finicky process, a process where as I change my optimization algorithm for my prior, I may get very different results. So what this motivated us, and this is joint work with Anat Levine, Marina Alterman, and Hen Bar, is to try to see whether we can explore these kinds of trade-offs and the effectiveness of this technique using Monte Carlo rendering. All right, same as throughout this tutorial. Now, here is the problem. As I mentioned earlier, all of these Monte Carlo rendering techniques only work for models that assume effectively geometric optics, whereas here, speckle is clearly a wave optical effect. It's an effect that lies completely outside the geometric optic approximation we have in the path integral expression I mentioned earlier. So what I will show you is how we came up with a technique that actually allowed us to simulate this kind of effect using very, very, very similar rendering algorithms to the ones that we have been describing so far in the context of geometric optics, correct? So, recap of what I mentioned earlier at the very start of the tutorial. Monte Carlo rendering basically says that I have a scene. In this case, my scene doesn't have surfaces, but it consists of a volume, maybe tissue. I try and trace paths through the scene. In this case, because I'm dealing with tissue, my paths will no longer just reflect on surfaces, but they will also potentially scatter inside the volume that I'm trying to simulate. And then I will accumulate through this path some contribution function that, as we mentioned earlier, includes emission and sensing effects, and also intermediate transport such as reflections, in this case, scattering effects, and so on. You can take a closer look in the context of scattering at exactly what contributes to this path contribution function. I will end up with a contribution that's very determined, very heavily dependent on the material properties. So between any two scattering events, I will have some free flight propagation during which light will attenuate based on the volumetric density of my tissue or other kind of material modeling. I will have some albedo parameter will determine whether my light will absorb or scatter, right? Whether it disappear or continue tracing. And I will have a property called the phase function, similar to the BRDF, that will say determine at what direction I will try to, light will continue traveling after a scattering event, okay? So all of this together determine my scattering material, which in turn determines the coefficient of, the contribution of any light path I trace through a scattering material. So all of this is for the incoherent case. Now, in the coherent case, as I mentioned earlier, we don't actually compute these integrals analytically. We actually simulate them using Monte Carlo by trying to import and sample paths that have very significant contributions to the camera. Now, in the coherent case, what we are initially interested in is simulating not the intensity of an image I would capture in this case, but the covariance of the speckle image. Because remember, the covariance, the autocorrelation is what I'm computing in the case of these speckle imaging applications. Now, it turns out that we can use theory from Maxwell's equations and some approximations like the ladder approximation and so on to rewrite all of these, the covariance expression for speckle images as another kind of path integral that looks like the one I have over here. That says that instead of just considering one path through the medium, and you take two paths and consider the complex contribution to the image, are now waves rather than just intensities. And then consider the product of these two wave contributions, the contribution between the two paths. Instead of just one image, I have different potentially illumination and camera, because I'm considering correlation of images across different viewing and imaging conditions. I draw paths for one imaging setting and another imaging setting. I compute their complex contribution to the path integral, and then I average all of this over a lot of randomly sampled paths, pairs of paths through the medium, okay? Now, since these are complex numbers, their product will also be a complex number with a phase. And for each one of the two paths, the phase will be proportional to the path. And for the product, the phase I will end up having will be proportional to the difference between the length of these two paths. But what's happening is that because I'm summing up a lot of complex numbers with roughly similar magnitudes, but phases that are essentially random because of this effect over there, what happens is that most of these paths cancel out. So I will end up with the contribution from most of the pairs of the paths I can sample being zero. And that's something I can prove. I can prove that in expectation, this contribution will be zero. So what does this say? It says that instead of considering arbitrary pairs of paths, I can consider only paths that share all of the nodes in between, except for the ones that correspond to the light source and the sensor that they start from, okay? So what this gives me is an algorithm that is very, very similar to the one I would have used for standard volume rendering, for standard rendering of geometric optics through this volume, but now to simulate not intensity, but covariance of speckle images. So I just produce paths exactly the same as before. I connect them to different lights and different sources, and I evaluate this covariance integral using some contribution for a pair of paths, for one path that's involved in the intermediate node that I can derive from Maxwell's equations and Fourier optics. So I end up with an algorithm that, because it allows me to ignore pairs of paths, has very low sampling dimensionality, and it's just as efficient as the algorithms that are used to simulate geometric optics. Okay, and now, in fact, once I have estimates of the covariance, I can also directly sample from its speckled fields. The reason is that the speckled images we are seeing have statistics that are dominated by their mean value and their covariance. They're Gaussian distributed. This is a classical theorem in statistical optics. So once I have this, I can actually go and directly simulate physically accurate speckled images for these materials using an algorithm that is essentially the same as the algorithms I used to simulate geometric optic scattering through volumes. Okay. So we had a paper with Hen, Marina, and Anat in 2019 that explains all of these details. And I'll show you just some validation here. So we were curious to see, is that actually true? Like, did we miss something in our math? Did we mismatch some of the terms we are using? Maybe we're ignoring some important effect. So to try to validate that this is actually correct, we validate in two ways. One is that we took wave optical simulators, finite element solvers, FDTD solvers, solvers for finite numbers of particles, and so on. There are a lot of numerical techniques for directly simulating wave equations. The problem is that all of these techniques, because they rely on discretization, they are excruciatingly slow. They're not scalable. To simulate something that's in the order of a cubic micrometer, you may need to wait for days to be able to get back some simulation result. Whereas what we have, because it's based on Monte Carlo rendering, it doesn't use any discretization. It's just as efficient as any other rendering simulation technique we have for, and it can scale up to very large scenes, can scale up to very complex meshes, and so on. So to see whether our efficient simulator matches the wave equation, we actually try to set up exactly the same scene for both simulators. Obviously, it had to be a very small scene because that's the only thing we could match with the wave optical simulators, and see whether we get the same result. And yes, we could actually able to exactly match the kinds of speckled fields and speckles that we could simulate with the wave equation solvers, albeit do that 5 orders of magnitude faster. And not only that, we also took a few materials for which we had known scattering measurements. We captured speckled images for those, and we saw that the statistics, we cannot match the exact same image of a scattering material without knowing its microstructure. But the statistics of the speckled images in that case match exactly those that are predicted by a covariance renderer. Okay? So this was, I think, one of the first demonstrations that I can use the same kind of Monte Carlo rendering algorithm we use for geometric optics to also render wave optical effects, in this case, speckled. Now, I'm not saying that this is a full simulator for wave optics, but it was still the first time we could show that we can accurately simulate wave optical effects using effectively a geometric optics path tracing Monte Carlo simulator. And going back to the fluorescent microscopy application I mentioned earlier, we can now go and start evaluating a lot of these parameters of these types of experiments virtually without having to do these experiments in the lab. Because as Aditya mentioned earlier, lab experiments are in general very tedious, very time consuming, non-repeatable, very hard to set up. So instead of having to do that, we can take our simulator and test out how different fluorescent microscopy techniques would work out for a lot of different types of materials, a lot of different types of imaging configurations, and so on. So we can, we can, for example, go and evaluate the memory effect for different types of scattering parameters, and potentially also even compare it with different types of approximations that people had proposed earlier, exactly because it was very hard to simulate this. So we can produce different curves for different evaluations of the phase function, different scattering densities, and so on. And not only that, but using this kind of capability, we also started thinking about different ways to solve this fluorescence microscopy problem. So how can I change, for example, my phase retrieval process to take advantage of local statistics of speckles, maybe some strong priors, and so on. So with this, we came up with a few different algorithms for solving the same kind of fluorescence microscopy pipeline that enabled us to do this kind of seeing through tissue and seeing through scattering experiments much more reliably than before. So these are real reconstructions where we take fluorescence particles, we place them behind chicken tissue, and we can get detailed reconstructions with our algorithm of what the illumination patterns that produce these speckled images much more accurately than with naive phase retrieval. Okay? And we can push this further. We now have this very strong signal, the correlation of speckled images, that we know also how to simulate and evaluate. So we can start using this for other tasks. For example, one kind of project that we have going on right now is trying to use this kind of speckled images to acquire scattering material. So the way this works is that we have a configuration like this. This is my student Bakari that's working on this. We place a sample in the middle, and we use this type of speckled images, speckled videos, together with some rendering post-processing of them to actually measure the optical properties of the small sample that we have placed at the center of our 3D scatter. Okay? So one thing I want to mention is that besides fluorescence microscopy and besides speckled imaging application, one kind of impact that this work had was start getting more and more rendering researchers to look into the simulation of wave optical effects. So since our original paper, both my collaborators and I have had several publications that follow up on it in the context of other speckled effects, but there have been also some amazing works in the recent 2-3 SIGGRAPHs that show how we can use Monte Carlo style simulators to get more and more complex wave optics effects. So I want to highlight here some work by Shlomi Steinberg and Lindsay Yan from UCSB. I think this paper was in 2020, and they have had some follow-ups last year and this year that show how we can also simulate diffraction effect, something that our simulator would not touch, but their simulator can now start to manage with geometric optic style techniques that are about as efficient as pure geometric optic simulators. Okay? So keep in mind rendering, physics-based Monte Carlo rendering, even if you are working with wave optics. We don't yet have the same kind of general capability as we have for geometric optics, but we are getting there. We can simulate speckle, we can simulate diffraction, we are getting more and more general rendering formulations. So any kind of wave optical system, imaging system that relies on wave optics, you should be able to have much better simulator tools to design and optimize it than finite element solvers that just do not scale. Any questions? Go ahead.
So this is like it's a really attractive sort of thing, like simulating wave optics on wave optics. Wave optics operators is pricey. What happens in your setting for fluorescence microscopy? The setting is basically like you either have dots or you have these sort of edge-only representations of space. What happens when you densify it and you try to do the same thing?
So that's exactly what we're trying to evaluate, how much you can densify these patterns and still be able to do a recovery. And the problems of the denser and the denser and the denser you make this, you end up basically blurring out your speckle, right? It says, think of it like this. I get speckle because I emit light from one point, from a laser. So I start increasing the emission area of that light. Effectively, I blur out the speckle from many different points in it until there is no speckle. So the same thing is happening in this fluorescence microscopy. The denser and denser I make these patterns, the less and less speckle I observe, and the harder it is to do anything. In fact, if you look at these are already, these patterns we're constructing here are already, I think, 100 times denser than what we could reconstruct previously with the initial phase retrieval algorithms before we're able to improve our algorithms using this rendering-based exploration. But yes, there are limits to this. We may be able to get to overcome even higher densities with better reconstruction algorithms. I don't know if that will be possible or not. What I know is that you can use the renderer to try and test such algorithms before you go out and do the real lab experiment, iterate over the design of better and better reconstruction algorithms. Maybe someone just wants to simulate a bazillion of these speckle images and throw them into a neural network that will do an amazing reconstruction. That may be a direction. All I can tell you is that you can at least, you have the renderer to do that. I expect there will be some limit, obviously. I don't know exactly where that limit is, but I hope that the renderer I show here should give at least a tool to make to explore the direction.
I guess sort of like part of the question was there's understandably like a limit to what you can do with exactly these kind of like base retrieval algorithms.
Yeah.
What you can actually reconstruct, but for the simulator side, is there a limit to? Can I simulate the speckle of a density even if it is a noisy blob, like a noisy mixed blob? Inaccurate noisy mixed blob? Or does the renderer also fall off?
No, the renderer in that case should not have a problem dealing with that. Well, let me caveat that. It's going to become slower in the same way that if you're simulating like a city style scene, because you have so many light sources, you end up with something in the rendering we call the many light problem. But we have ways to deal with that, and it's still going to be way faster than like a discretization-based finite element wave simulators. But its accuracy should not fall off. It will just become slower. Yeah. Any other questions? All right. So that's all I wanted to say about speckle imaging and, as I mentioned, more generally, wave optical simulator. I'm going to move on to a different kind of design problem again for a very, very, very different type of sensor called vision-based tactile sensor from robotics. And this is joint work with Ted Adelson and Vincent Yan at Carnegie Mellon University. So Vincent and Ted, they are experts. Well, Ted is an expert in a lot of things, but both of them are experts in tactile sensing, in particular vision-based tactile sensing. Now, why do we care about tactile sensing? Because in robotics, we can use this to do a lot of perception, manipulation, to create neuroprosthetics, to do advanced manufacturing. It's a very useful sensing modality if you go outside of computer vision and look at more general automation robotics tasks. And because of this utility, there is a very large array of tactile sensors available. I will admit I don't really know much about most of them. There is these ionically conductive fluid-based techniques, magnetic field-based tactile sensors. The ones that I am more familiar with through my collaboration with Ted and Vincent are vision-based tactile sensors, gel side. So, and this is really what we'll be focusing on in the rest of this tutorial. So just very quickly go over what gel sight is. So gel sight is a sensor that Ted Adelson and Kimo Johnson invented in 2013, not 2021, that works as follows. I have some elastomeric material, basically a material that can deform, and it's diffuse, it's very Lambertian, okay? So then I place a camera and a light behind that, and I get the elastomeric material and I use it to touch the surface that I want to scan. So my sensor gets some images like the ones that we see on the right over here. So as I touch, I observe a deformation over there. I think this is not playing anymore. Yeah, I see a deformation right there that gives me some information about the shape. Now, because this shape is Lambertian, I can very easily convert that to shape information by just running photometric stereo. So I have normals over here. I have different images from different illumination conditions. I can run some photometric stereo shape from shading procedure and get back out of this some very high detail normal and surface information. So in a sense, I'm using the information from a camera to convert that into tactile information about the surface that the elastomeric part of my sensor is touching, right? So I'm using, even though it's a vision-based sensor, I get back the kind of tactile feedback that my sensor is after. So since Ted and Kimo introduced this in 2013, there has been a very large, it's become a very active area of research, and there have been many different iterations of vision-based tactile sensors. So there are flat gel, there are finger-based round tip sensors, and so on. So the problem was that all of these have different trade-offs, and they're hard to design and optimize for different sensors, which is where I came in. So at some point, Vincent and Ted came to me and said, look, we would like to be able to use OptiCU simulator to make the design of tactile-based or vision-based tactile sensors better and easier. And of course, the reason why, given that these are vision-based tactile sensors, the kind of simulator we need to be able to facilitate their design is rendering, the simulating of light transport inside those. Now, it turns out that this rendering task is a very difficult task. It's actually a very, very hard kind of situation for physics-based rendering algorithms to handle, and I'll go over why that is, okay? So, designing vision-based tactile sensors using rendering. Now, very hard task, not only because of the difficult rendering problem, as I mentioned, but also because we have such a high diversity of sensors we can think about. You can really take any possible shape you can think of, apply some elastomeric material around it, and make it a tactile sensor. So which one works better? We don't know. And it's really hard to explore this kind of design space through real experiments, real prototypes in the lab, given how vast it is and given how slow the prototyping process and the lab-based process is. And not only that, as I mentioned earlier, we actually have very, very, very complex light interaction in these kind of vision-based sensors. And I'll try to demonstrate that for a specific vision-based tactile sensor that has been the focus of my collaboration with Ted Benson and Arpita Graval, which is the student that is working on this. So these curved tactile sensors, they look kind of like this. So this is a 3D carve out of them, where we have several layers of different materials, all of which coming together to form a surface, a curved surface that the camera is looking at. And then what's happening is that this combination of different layers ends up acting as a waveguide. Effectively, what I want to make sure is that all of the surface that I can use for my tactile sensor will be illuminated. So by squeezing together some piece of glass between some semi-reflective surfaces, I can ensure that light will travel throughout the elastomeric surface so that my camera can always observe the deformation that can happen when this surface touches a material. So I have over here some light or some rays that my camera will receive, which will first scatter at some intermediate frame, and then they will bounce several times until they reach a light that's placed at the bottom of this sensor. So it kind of works like a fiber where I have multiple bounces of light between two materials until I encounter some deformation that would then form the image in my camera. Okay, so I have this complex light matter interaction process that I want to optimize for different types of parameters, for sensor geometry, for materials, for the placements of camera and lights, and so on. I think there is some question in the chat. I'm seeing a post over there.
Yeah, the question is, perhaps I missed it, but I do not see any mention of phase of light, nor phase angle.
So I did understand that? I mentioned, I'm guessing that with respect to the previous application I was talking about in speckle imaging, but I did mention phase there when I was talking about the correlation of pairs of paths and how they contribute to the image, and how the fact that pairs of paths that have very different path lengths will end up canceling out exactly because we are summing up complex numbers and the phases are random. So yeah. Okay. All right, so we have this complex optical system that we're trying to optimize with respect to both sensor geometry, material specification, placements of cameras and lights, and so on, and try to extract out of that very, very, very detailed tactile images. Now, why is this a hard rendering problem? When I get specific, like nail down exactly the kind of effect that is really hard for rendering algorithms to simulate. So we can think of different types of reflections that happen in scenes and classify them as relatively easy to deal with rendering and relatively hard to deal. For example, if I have a diffuse surface that just scatters in all directions, this is an effect that's pretty easy to simulate with Monte Carlo rendering algorithms. If I have a sequence of specular reflections, so light passing through several pieces of glass and mirrors, smooth glass and smooth mirrors, that's again a kind of interaction relatively easy to render. But relatively easy to render, what I mean is that, remember, in rendering, in physics-based rendering, we randomly sample paths, and we try to make those random paths be paths that have high contributions, that will contribute a very large amount of light to my image. So for these types of effects, it's easy to come up with sampling processes that will achieve this. But there is another kind of interaction, another kind of sequence of reflections and refractions that's actually very, very, very difficult to randomly sample. And this has to do with paths like these, paths that go through specular reflections or specular refractions, and between those two, they have a diffuse reflection. So these are called SDS light paths, specular, diffuse, specular. They are one of the hardest types of effects in geometric optics for Monte Carlo algorithms to render. And really, they are at the core of rendering, the core of the challenge of rendering these tactile-based sensors. So we want to make simulators that, among other things, among other SDS type of paths, can allow us to produce physically accurate images of vision-based tactile sensors, and also allow us to optimize these sensors to achieve improved performance with respect to different tactile sensing tasks. Okay. Now, exactly because of this SDS type of light path, we cannot use algorithms such as path tracing, bidirectional path tracing, light tracing, ray tracing, the very first iteration of Monte Carlo rendering techniques. Instead, we have to use another class of techniques called Markov chain Monte Carlo. They are still Monte Carlo rendering techniques, but they generate paths in a very different way. Whereas path tracing and bidirectional and light tracing create paths independently. Every path is traced, gets to the camera, thrown away. Another path is traced, get to the camera, thrown away. Markov chain Monte Carlo techniques create correlated paths. They take one path, they make a small change to it to produce another path, and so on and so forth. And there is some reason, some theory behind why all of that is the case, but the reason is that in the end, they allow us to sample very difficult, very rare paths, including the ones that include SDS interactions, okay? Now, these techniques have a long history in rendering. They have been introduced in the late 90s by Witz and Guibas in the context of metropolis light transport in order to deal with other kinds of other places where these effects show up. For example, rendering the caustic of a bottom of a pool. That's a classical case of SDS paths. But this was a really interesting project to me because it was a case where I could actually take this very difficult and maybe niche path and use it for a scientific imaging application such as the tactile-based sensor we're showing here, okay? And in particular, what we ended up using for these types of paths was a kind of Markov chain Monte Carlo algorithm that we developed together with Kavita Bala, Shuang Zhao, and Fujun Luan at Cornell that we call Langevin Monte Carlo. I'll very briefly go over that because I think it's an interesting type of stochastic sampling technique, especially for real working computer vision. But at the end, the application is going to be focused on vision-based tactile sensors. Okay, so I'll do a small detour on Langevin Monte Carlo before coming back. So what is the idea behind Langevin Monte Carlo? Langevin Monte Carlo, it has to do with the fact that I can take optimization algorithms and convert them to sampling algorithms. Remember that the problem is we need to come up with a way to very effectively sample rare paths, paths that have very high contributions to the camera, but are very few and far in between, okay? So I'll try to do that by creating sampling techniques that look very similar to optimization algorithms. How does that work? Optimization and sampling, at first, they may look like very, very, very different algorithms. So let's look at how optimization, in particular gradient-based optimization works. I have some latent space x, and I'm looking to optimize some function f of x, right? How do I do that? Well, I go and compute gradients of this f, and I form a path that will, and I make steps along this gradient. So I keep doing that until I get to a point where I have values that, values of x that maximize or minimize the function f that I'm looking to sample, okay? I have some scalar step size or other step size if I use Adam or any other kind of algorithm, but the key idea is that I follow the gradient of the function I'm looking to maximize. Now, in sampling, what we are saying is that I don't want to maximize this function. I want to create random samples for it such that I will have a probability of selecting a point x that is proportional to f. Why do we need that? Because remember, in rendering, what we are doing is that we are sampling paths, x in that case will be paths, that we are hoping will have a high light contribution, which correspond to the function f. And then how can I use gradient descent to do that? I can use an algorithm called Langevin Monte Carlo that is the following. Start from some random path, make a step, same as you would do if you were looking to maximize this function f. So make a step along the gradient direction, and then add some noise. Accept or reject this step using the Metropolis-Hastings rule. If you end up adding so much noise that your sample became very bad, just reject it. If not, keep going, and then iterate. So I keep doing that, and I end up with a sequence of paths. So what does this say? so long as I have a differentiable function, and in this case, the contribution of a path is actually differentiable, then I can take any gradient descent style optimization algorithm and turn it into a sampling algorithm. And remember, in the context of rendering, sampling means rendering algorithm. I have a way to generate high contribution paths. I have a way to form images. Okay, so I can take any gradient-based optimization algorithm, Adam, I don't know, ADAMAX, Momentum, RMS, Prop, and so on, and convert an equivalent sampling algorithm that can implement inside my Monte Carlo renderer to form images, even in the presence of these difficult caustic effects that I cannot generate otherwise. I'll show you a couple of examples of these, not yet the tactile sensors, just to show you the difference it can make. So here are some examples where we sweep between previous renderings and our. Let me do that once more. Where you can say that at equal time, we can get 10x reduction in variance, basically a 10x acceleration in a renderer. And here is another scene which is really, really dominated by these SDS paths, by caustics, where we, by using the Langevin Monte Carlo, we can get a 20x acceleration. Now, these are not the scenes that we developed this algorithm for, but they do contain a lot of these specular, diffuse specular paths that are really the key challenge in simulating tactile-based vision sensors, vision-based tactile sensors, excuse me. Let's go back to this. Go ahead.
You turn the optimization algorithm into the rendering.
The sampling algorithm. Yes, I will use for rendering, yeah.
But you said you were maximizing or minimizing some function f of x.
The function being the throughput function. Now remember that every path has this contribution function, the sequence of BRDFs and geometry terms and so on. So maximizing that, or trying to sample proportionally to this function, trying to sample paths that have high values with respect to that function. But I will not quite maximize it because remember, I always add some noise, right? I make a gradient step, and then I take noise.
So it's a fixed function for any SDS optimizer.
It's a fixed path for any path. For any path, I can write it down for any light path, including paths that have SDS.
I see.
Okay. It's if you go back to the very start of the tutorial, it's the function I showed that involves emission, sensitivity, BRDF, and transport along a segment. But still a function I can write down and differentiate. So I can both maximize, which is not what I want in rendering, and also use the random version of kind of like stochastic gradient descent to draw samples from. Go ahead.
So when you generate the path, you the electron port again, because you might get a pretty high frequency effect, like you might go in and out of shadow.
Yeah.
You're ready.
Yeah, so I'm gonna, well, I mentioned earlier over here that there is this Metropolis Hastings steps. Basically, that's an acceptance or rejectance. Did the new path I make is the new path I make good enough? If it's a very, 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 very bad path, then almost certainly I will reject it and I will go back trying to generate a new one. But if it's decent, then I will accept that path and continue.
Don't you introduce bias into your sampling if you do that?
No, so I don't introduce bias because at the basis of all of that, what's happening is that I'm running a Markov chain Monte Carlo process, which is a general sampling process that after some burn-in operation can give me unbiased samples. Okay. Any other questions? All right, so going back to vision-based tactile sensors. This is an image from a real prototype that our Pete built. This is the kind of rendering we get if we use rasterization. We get nothing because rasterization cannot model specular diffuse interactions. This is the kind of rendering that we get with path tracing. Now, in theory, if I let path tracing run for infinitely long, it should be able to get me a correct image. It's consistent in a sense, and it is also unbiased, except that for speckle events, it will have almost near zero probability of sampling them. So it cannot give me an accurate image in this case. And this is the kind of images that we can simulate. This is not exactly matched to this prototype, I should say, so they don't look identical, but I can start looking at these effects. So later iterations, after we measured all of the optical properties involved in this pipeline, we actually matched the exact image that we capture with those, thanks to the fact that we can use this Langevin Monte Carlo and Markov chain Monte Carlo rendering algorithm. Okay. So it gives us now a nice tool to try and evaluate different sensor designs. which is exactly what we have done. So we've run a lot of simulations to evaluate different sensor materials, how to make the different patterns, different sensor illumination, different camera placements, different shapes for this elastomeric material, basically the surface of the artificial finger we are making, and evaluate all of these completely based on simulated experiments without having to fabricate every intermediate proposed sensor. And in the end, after we converged to some optimized design, we fabricated that and we used it together with robotic graspers to do much better handling. So here you see cases where we use this tactile sensor to image these Legos or get very high detailed images of keys or like rotate the cap of this mustard bottle, or even use the sensors to do tasks such as surface inspection. So one common application of this tactile sensing technology is to try and mimic reading inscriptions using just the tactile sensor. So, and we can see that with the unoptimized design, we get very, very, very inaccurate readings, whereas with the optimized design, we can greatly improve, though not yet perfect, the kinds of readings we get in this case from the tactile sensor. So all of these are improvements that we get thanks to the fact that we can optimize our sensors using these rendering algorithms I mentioned earlier. A few more examples of the same application and a last video for surface inspection. Is that not playing? Where we are slowly moving this robotic arm on the left to go and visualize again through the effectively a tactile sensor, all of the text in this surface. Okay, so any questions while this video is playing? All right. So this was the last example of some forward rendering modality we have used for some imaging applications. So we've gone through time of flight, no line of sight imaging, acousto-optics, ultra-fast lenses, spectral imaging and fluorescence microscopy, tactile sensors. So the last thing that we're gonna go over in this tutorial is what I write here is inverse rendering. How can I use rendering to now solve problems where I'm trying to infer unknowns about a scene from image measurements? And we'll see one key technology for trying to make this possible, which is called differentiable rendering. And differentiable rendering is something that has gotten a lot of attention in computer vision in the past 3-4 years. Our focus here will be primarily on Monte Carlo, physically accurate differentiable rendering that can handle global illumination and different types of imaging related applications that we have used this for. Okay, so just to reiterate, forward rendering is the process of taking a known scene, and by scene I mean everything from geometry, materials, sensors, lighting, everything specified, and producing from it a physically accurate image, or at the very least physically accurate to the point I care. If I care about wave optics, I need my image to show those wave optical effects. If I'm operating the geometric optics regime, then I'm okay with a simulation that reproduces all of the geometric optics effects. Inverse rendering is exactly the opposite process. I'm gonna try and go from image measurements to some unknown about my scene. And how general this unknown is gonna be will depend both on the application context and also the types of measurements I have. For now, just leave that abstract just to explain what inverse rendering is and how it works. But I could imagine that I'm optimizing for geometry, materials, cameras, just some unknown in my scene, okay? Now, this is a very general problem statement. Basically, all inverse problems in computer vision fall under that. Inverse rendering refers to a very specific methodology for solving these problems. It also goes by the name analysis by synthesis. Depending on your background, like I think in computer vision, this is most often called analysis by synthesis for historical reasons. In computer graphics, it's most often called inverse rendering, but at the end of the day, it's the same methodology. So what this says is that I will try to infer the unknowns in my scene by solving an optimization problem that says, find the values for these unknown parameters such that if I use them to render images, I will match my measurements. or I'll match my target. The images I'm given as input may not be measurements, or maybe some target set of images I want to produce. Okay. So this image function is exactly the rendering process, the light transfer process we mentioned earlier, that we can simulate using physically based rendering. And the target is some captured image, some image I'm given as input. So this optimization problem is specifically the inverse rendering / analysis by synthesis methodology for solving inverse problems. Okay. Now, if I can try to solve this with some gradient-less procedure, but in general, that's very expensive because what I end up having to do is exploring very vast parameter spaces. If I'm looking to optimize over a shape, there are really infinitely many shapes I can use to match my images. And also because that involves a lot of forward operations to evaluate the image model and some loss value for my optimization function. And these, excuse me, rendering operations are actually pretty expensive. So this approach just doesn't work. Instead, what we can do to accelerate analysis by synthesis is change how we use our renderer. So instead of trying to optimize this problem using gradient-less techniques, we'll use gradient-based optimization, the most efficient way we have for optimizing relatively smooth loss functions. And of course, gradient-based optimization requires that I have access to gradients of losses. I will use my renderer to actually compute these differentiable losses. Why do I need a renderer for them? Because remember, this loss involves the light transfer process itself. It says, take some parameters, run a physical simulator of light transfer to produce images. So we want to differentiate this process to get back to sensitivity of the image we produce with respect to some unknown parameter. Okay? And then in this context, I can now try to solve inverse problems that involve unknown illumination, unknown material parameters such as reflectance, scattering, unknown scene parameters like camera pose, shape, an object location, and so on. So I would like to be able to do differentiable rendering in a way that is essentially as general as our forward rendering simulators, in the sense that they can handle arbitrary global illumination effects and also arbitrary scene specifications. Scene specifications at least of the same complexity as the ones we can use in forward Monte Carlo renderer. Okay, and plugging that into an gradient descent, we'll use all of our compute to do this for different compute the gradient step I need for my gradient descent operation. So that's our setup: inverse rendering, the types of problems we want, and the desiderata we require for our differentiable renderer. Now, how do I actually do that? Remember that what the renderer does is evaluate this very complex, okay, not necessarily super complex, but this involved light transfer model where there are paths that have BSDFs and geometry terms and visibility terms. How do I actually differentiate through that? And the key here is to notice that effectively what I'm looking to do is differentiate an integral with respect to some unknowns that show up in both the thing I'm integrating, the integrand, the function inside, and the integration space, the space of light paths. So I'll try to give you some high-level understanding of how differentiable rendering algorithms work. And for that, I'll start from some reminder, or at least some presentation of some basic calculus materials about how we differentiate functions that have integrals. So that's just to give you some insight of the key challenges and the key algorithmic innovation in differentiable rendering. Okay. So let's say that I have a function like this. Forget about, for now, about rendering. I just have some f of x and also some other parameter pi that I need to integrate from a of pi to b of pi. And I want to differentiate this with respect to this pi parameter. What's the result? What's the derivative? So I can use a nice rule from calculus called differentiation under the integral sign, or the Leibniz integral rule, to write out this derivative as a sum of three terms. And these three terms are as follows. The first one says just move the derivative inside the integral, right? So just differentiate the integrand, the function f I'm integrating. The second term says that, my integration limits also depend on this pi. So I need to go and differentiate those as well. So basically differentiate A of t, differentiate B of pi, A of pi, excuse me, B of pi, and evaluate the function I'm integrating over there. And lastly, there is an extra term over here. If my function f is discontinuous anywhere between A and P, I also, and this discontinuity depends on the parameter pi that I'm differentiating with respect to, I also need to include that there. That, cannot forget about that, it's very important. Okay? Simple calculus. Just an example to make sure that everyone absorbs this. I have to differentiate this function that shows up all of the problems we had before. The function that's discontinuous at some location 2 pi, and I'm integrating from 0 to 4 pi. For differentiating with respect to pi, I first have the first term, which is move the derivative inside the integral. Then I have the second term, that's differentiation of the integral limits. And then I have a third term that accounts for the fact that I have a discontinuity at 2 pi that depends on the parameter I'm optimizing over. Okay? Any questions so far? All right. So Leibniz integral rule, and we'll split these two terms for the rest of the talk into the interior integral, as we'll call it, basically just move the derivative inside, and the boundary terms, everything that has to do with the fact that we have discontinuities and integration limits that depend on pi. Now, this is for simple integration on the real line. To do differentiable rendering, we'll need, remember, rendering, you can think of as evaluating an integral over a complex path space. So what we'll try to do is take this differentiation rule and apply it to that very complex path integral. So to do that, we'll use not the Leibniz rule, but the like a higher dimensional version of this called the Reynolds transport theorem. One note here, transport in this context has nothing to do with light transport. It has to do with terminology that comes from shape optimization, but that's the name of the theorem. And this says that if I'm integrating some function f over any arbitrary domain, some surface, some volume, anything, I can use something similar to the Leibniz rule to write down my derivative as a sum of two terms. One where I'm just moving the derivative inside, and one more where I'm taking into account changes in the domain of integration and any discontinuities. So I have this boundary domain that is just the combination of both discontinuities and the boundary of my integration domain evolving over pi. So for example, if I'm integrating this function f equals 0 or f equal to 1 over this area, and I'm moving, the boundary of the domain will be this omega, the discontinuity point will be in the center, and as I'm changing pi, my derivative will depend on both the interior and also this line that I get because of the discontinuity points. Interior and boundary integral. So now that we have this, we can take this more general differentiation rule and start applying it to the kinds of integrals we see in differentiable rendering. Differentiate it, and then estimate them using Monte Carlo path tracing, Monte Carlo light tracing, same as we did before. And I'll go through one more example now. Again, I won't go through the full differential rendering formulation because it's pretty complex, but I'll work step by step through the direct illumination of it. The case where I have light, only leave a light source, interact with my scene one and go straight into my camera, and see how we can use this differentiable rule in that context to derive a differentiable algorithm. So, direct illumination integral. I have some point x where I'm looking to measure the outgoing radiance from that, and I'm receiving light from some scene like the one I'm showing here. Because I consider only direct illumination, meaning just light that goes into the scene, reflects, and then goes into the camera, I can simplify the complex path space integral, so the start, to something that looks like this. So what do we have here? We have an integral over all of the directions omega around x, right? And then along all of these directions, I'm summing up incident light, how much light this point is receiving from a light source from direction omega, how the reflectance, how much light's going to reflect towards the direction from which I'm observing x, and then some term that has to do with foreshortening that comes from the rules of radiometry. Okay? So in Monte Carlo rendering, the way we evaluate this integral is by drawing random samples of the variable that I'm integrating over, and using their sum to estimate, their weighted sum to estimate my quantity. In this case, I'm not randomly sampling paths, I'm just randomly sampling directions. So I can estimate all of this by randomly selecting some directions omega from some PDF and forming an estimator like this. It's exactly the same story as the one we started from in this tutorial, except applied to the simpler case of no global illumination, just direct illumination. Okay? Now, let's see how we differentiate that and how we differentially render this expression. And I'll start with a case where I differentiate with a set of parameters I like to call local parameters. As parameters, let me simplify the Reynolds transport theorem. For example, these include the BRDF at the point X, the shading normal, the illumination brightness. Basically, these are going to be parameters that don't deform any shapes in the scene and they don't move things around. So in this case, the differentiation of this direct illumination integral is pretty simple. All I have to do is move my derivative inside, okay? And now how do I estimate this? I have another integral that I can evaluate in exactly the same way as I evaluated the initial direct illumination integral. I will go and sample some directions omega, and for those random directions, instead of computing, not estimating, the product of BRDF, LI, and for shortening, I will compute the derivative of this term. And since these are analytical functions, I can easily differentiate, okay? This is a very simple case. Effectively, I end up with an algorithm almost the same as the Monte Carlo one I used for the initial direct illumination rendering to get an estimate of the derivative of this image with respect to pi. There is a trick here, and it has to do with the fact that generally, the PDF I use to sample these omegas, these directions, because I want to make it match the function I'm integrating, will also depend on this unknown parameter pi. So in that case, I can, instead of just differentiating the numerator, differentiate the ratio of these two, differentiate both numerator and denominator. So this gives me an alternative estimator that has also been studied very well recently by Zeltner and Wenzel Jakob and his group. And which of the two you want to use, both of them will give you correct results, will give you unbiased results. Which one is going to be more efficient in the sense that which one will result in less noise for the same amount of compute will really depend on the scene. But you can consider a lot of them. In fact, there are a lot of tricks like this we can do to come up with a very large array of estimators for these, of differential estimators for these kinds of parameters, pretty much how in the initial Monte Carlo rendering we started by coming up with different sampling techniques. We can get the same path integral framework to give us very different estimation algorithms. We've already seen path tracing, light tracing, Markov chain Monte Carlo, and so on. Okay, so very active research area and very large design space for algorithms. Any questions? Go ahead.
Question about the Reynolds transport theorem slide.
Okay.
So that there is a function G, but what is G?
Yeah, so I didn't mention that. That G has to do with the normal derivative at the point of the boundary you're evaluating. So that point is going to move along some direction, right? So take that movement, that velocity along the normal, and you multiply it by the integrand, the function you're integrating. Okay? Any other questions? Okay, so I go solve for these local parameters. The parameters are, let me just move the derivative inside. And again, think of them as things that don't change the global scene geometry. They don't move things around, don't stretch or deform shapes, they don't do anything. But in a lot of interesting problems, we actually have to deal with these kinds of parameters. We have to optimize for shape, for camera poses, and so on. So in this case, what do? We cannot just move the derivative inside. Because remember, now my domain of integration will either explicitly depend on pi or will have discontinuities that depend on the unknown. So instead of that, I need to use the full Reynolds transport theorem. And let's try and apply this to this case. So if I look at the thing I'm integrating, which is in this case the incident illumination times a BRDF, for this scene, it will be discontinuous with a discontinuity that depends on the size of the emitter. So if I'm trying to optimize with respect to my emitter, this is discontinuity I need to take into account, okay? If my unknown is exactly stretching or compressing this emitter, because that induces a discontinuity in my integrand, I need to take that discontinuity into account. So I will end up differentiating this and getting two integrals I need to estimate. An interior integral is pretty much the same as the one I saw for the local parameters, and an extra integral that says go and integrate along these discontinuities. Okay? It's pretty bad because, first of all, I have two integrals now, not one, as I had throughout. And not only that, I need to go and sample points along this very narrow red line. Now we'll see how we can work around this. Just keep it in mind, it's non-trivial, it's very difficult. I can also try playing other tricks. For example, instead of writing this as a direction over, as an integral over directions, I can write as an integral over points. Look at all of my points around the scene and grab from each one of them the light contribution I have. So I change my directional integral to an area integral. This is actually something that we do very commonly in physics-based rendering. We change the domain of integration from one to another. And now I have some extra function that includes visibility terms, fall-off, foreshortenings, and so on. The problem now is that I no longer have a discontinuous integrand, but what I did is that I made my domain of integration depend on this parameter I'm optimizing over. So I still have the same problem. If I apply over here, I have a continuous integrand, but I have a parameter-dependent domain of integration. So if I apply here the Reynolds transport theorem, I again get this interior and boundary domain. So the fact that I'm going to have to deal with these two integrals, and especially the boundary one, is not something I can easily escape. I will have to deal with it one way or another, at least if I care for my derivatives to be accurate. Okay? So whether you use hemispherical or area, in both cases, you end up with these extra terms. Now, what effects in IC can cause these extra terms to show up? Anything that's dependent, any parameter that affects either boundary edges or sharp edges or visibility changes will cause these discontinuities. So if I have, for example, some source and I'm expanding or contracting it, I'm trying to figure out its size, its boundary will be something that I need to include in this derivative integral. If I have some shape that's discontinuous, and as I deform the shape, I move the discontinuity, I move the edge of that cube, that's going to be part of my boundary integral. And then probably most annoyingly, because in rendering, I have to evaluate whether a ray can reach another point or whether it's visible or not. If I have anything that changes this visibility, I will end up having to compute an integral over the places where visibility changes, the silhouettes of objects. Okay? In fact, these last type of visibility-driven techniques are very persistent. And even if I change my geometry to be smooth geometry, like a neural network or some SDF or other kind of implicit function, I will still have to deal with these visibility-driven discontinuities if I want my gradients to be physically accurate. Okay? And in fact, for a lot of tasks, you may not need to do that. You may just ignore these visibility discontinuities. In other tasks, depending on exactly the kind of detail you are looking to capture in your differential rendering technique, this derivative integral may actually be the most important part of the gradient you're estimating, like shown here. And then one of my colleagues, Shuang Zhao, they had a paper where they were showing that it actually matters a lot, especially for 3D reconstruction techniques, to be able to accurately model these kinds of visibility gradients if you want to get very high quality 3D reconstruction. That's, again, not always the case. Depending on your application, you may be able to just stick with the first type of algorithm, or you may have to use very accurate visibility gradients. It will depend on exactly what I'm trying to do. Okay? So all of this was just for direct illumination. So we're still not done with the full differentiable rendering algorithm. If we want to deal with global illumination, we need to take all of that and apply to the case where light can now bounce in the scene a lot of times, several times, potentially infinite times in theory, even though we never actually deal with that. So how to generalize these ideas to the global illumination setting is a very active area of research. There are a lot of papers that have come up in the past 3-4 years, like path replay back propagation, warp space reparameterizations, applications to different types of surface representations, like neural SDFs or other kinds of implicit functions. I'll highlight one that we have developed with some colleagues, with Shuang Zhao and Cheng Zhang from UC Irvine, with my student Bailey Miller, that tries to mimic the path space view of light transport that we started this tutorial with. Remember this path integral, this says that I can write images as an integral over this weird path space, basically the space of all light paths. You can prove that if you apply the Reynolds transport theorem, you can write derivatives of global illumination as sums of two other integrals. And this is a very involved derivation. I'm not going to go through them. I'll just look at exactly what it is we're integrating. One integral is exactly the same space as the one we used for light paths. So basically, it says go through all of the different light paths and sum across them some slightly different function than the one you will be summing up in forward rendering. And the second is a special space of light paths that says that one vertex in my path needs to correspond to one of these discontinuities that I was describing earlier. For example, I need to make one vertex in my path, one segment in my path, be passed through a visibility silhouette, and all of the rest I can trace exactly the same as before. Okay? And now, since I have these path space integrals, I can derive for them path space integrators like path tracing, bidirectional path tracing, and so on. So I can take all of the different estimators I have available for me for forward rendering and convert them to unidirectional and bidirectional estimators for the boundary space integral. So this gives me a very, very general set of algorithms that I can use to compute these derivatives with respect to different types of parameters while also taking into account global illumination. Okay, so any questions? All right, so I'll show a few applications of this, and including some applications will actually require us to further generalize these rendering algorithms to deal with more and more complex rendering effects, such as some of the stuff that Aditya mentioned earlier. Now, one thing I'll say is that especially differentiable volume rendering is something that lately has gotten a lot of attention in computer vision, especially neural rendering. Like NERF effectively is differentiable volume rendering, except that we don't consider global illumination, we just consider single scattering. In fact, in NERF's case, we don't even consider single scattering, we consider just emissive, just absorptive volume rendering. And there are some generalizations for that to go one step further. I won't talk about these applications. I'm pretty sure there are a lot of tutorials and workshops running right now at CVPR going about this. I'll focus at cases where we actually need to deal with global illumination because that's where all of our signal is coming from, or where most of our signal is coming from, and because we are looking to do recovery at the kind of fidelity we can just not ignore the signal. Okay, so one case, and this is actually how I started working in a differentiable back in 2013, is the problem of acquiring scattering materials. So if you've done any work in modeling materials, you may know of a lot of techniques for modeling reflectance properties, for reflectometry, acquiring BRDS. So one of the things that we wanted to work on back in the day was, how can I do the same, but for material that have scattering? How can I acquire the scattering properties of a material that has very, very strong subsurface scattering? And by that, I mean things like the volumetric density, the albedo, the phase function, all of the parameters I mentioned earlier when I was describing speckle. So in the context of this, we came up with what I think was the first Monte Carlo multi-bounds differentiable rendering algorithm, exactly for this problem. And we couple that with a very simple acquisition setup that works like that. We have a camera and a laser. We put a sample in the middle. This is a sample of milk. And we move the camera and the laser everywhere around it to capture images that look like these blobs at the bottom. And then once we have those, we can plug them into an inverse rendering problem that we solve using gradient-based optimization and differentiable rendering, where we now take into account all of the different bounces, global illumination and global subsurface scattering. And if we do that, we'll recover a set of optical parameters that actually make it possible for us to very accurately reproduce the appearance of these materials. So for example, we had scanned different types of soap, olive oil, blue curacao, a non-alcoholic version of blue curacao, whole milk, and so on. And we saw that we could actually recover so accurate optical properties that we could go back and produce very photorealistic images of these materials. These are all synthetic images of stuff that I had 3D scanned with this kind of pipeline. Now, besides olive oil and whole milk, you can actually, this is a very important problem in science, in material science, in chemistry, and so on. For example, there is this version of this problem called particle sizing, where we have liquids that include inside them very, very, very different and small particle materials. They can be titanium dioxide, they can be aluminum oxides, different chemical materials. And we want to be able to characterize the distribution of these types of materials. In fact, it is such a big industry that there are a lot of different dedicated devices trying to solve this problem. And not only that, but NIST has, a set of ground truth materials, effectively, materials that are fabricated with very, very, very well characterized distributions just to test the accuracy of these devices because of how widely they are used in material science, in fabrication, and other critical areas of technology. So what we found was that we would actually take some of these ground truth polydispersions and scan them with our very simple technique, or very simple setup, and actually produce much more accurate fits than a lot of these industrial level particle sizings, exactly because our differentiable rendering algorithm could capture global illumination effect. Whereas all of the previous techniques for doing this kind of particle sizing typically limit themselves to single scattering, direct illumination only, exactly because it's very difficult to differentiate or otherwise invert the global illumination process. Okay? This goes back in 2013. Since then, scattering has been a core area of application for these differentiable rendering algorithms, exactly because it's a case where we really have to deal with global illumination. It's a case where I cannot work around by just ignoring any light besides the single scattering. So we have seen stuff for optical tomography. There was a lot of follow-up work on figuring out materials to do 3D printing. So if you're fabricating some object by depositing little amounts of different inks, you want to figure out what is the optimal combination of inks I can use at every voxel so that my object will have a specific type of appearance. That's an inverse rendering problem that involves global illumination, and I can go and solve that inverse problem using differentiable rendering. And then other applications, Yoav Sekner's lab has a lot of application on cloud tomography, computed tomography. At Cornell, Steve Marsner, Kavita Bala have been working a lot on characterizing fabrics and so on. All of these are cases where we have to use not only differentiable rendering, but differentiable rendering can handle global illumination, because that's the only way to obtain very accurate characterizations of the materials that we are looking to measure, reproduce, analyze, inspect, and so on. Okay? Another set of problems I will show are different versions of 3D reconstruction. Again, a lot of work on that in computer graphics. I'll focus in, computer vision. I'll focus in a few settings where we have to work explicitly with global illumination, higher order bounds. One is the non-line of sight imaging case that Aditya mentioned earlier. I'll briefly go over that. Basically, we want to figure out shapes of hidden objects that are hidden from the camera, potentially most commonly using time of flight measurements. So we can, in this case, extend our differentiable renderers to the case of time of flight measurements, like the ones we capture from a SPAD-based light. And then by setting up an inverse problem, we can get very detailed reconstructions of hidden objects because of the fact, and I have our differentiable renderer optimize the unknown shape to very, very accurately fit the parameters that we are measuring. In fact, I should say that this is a case where we don't actually use full global illumination, but we still have to use up to third or fourth bounds, depending on the kind of accuracy we need. And even that can give us very, very, very big improvements in terms of the kind of reconstructions we can do. Here is another case, very different from before. So this is joint work with Michael Kais and Mohammed Kadri. They've had a paper at ICRA this year where we're looking to do 3D reconstruction using imaging sonar underwater. So underwater, because water is dirty, especially if you're working at very busy port environments, it's very useful to be able to image using sonar rather than light, because sound can travel through it can have much longer propagation distances. So what we've been trying to do is see if we have robots that can navigate underwater and are equipped with sonar, whether we can use these very diffuse, very non-localized sonar measurements to actually get detailed 3D reconstruction. So this is what this looks like. This is the robot from Michael Casey's lab, where it's navigating along this, the high, we call it the high bay at Carnegie Mellon. It's basically a tank where you can submerge anything inside and make the water as murky as we want to imitate different marine environments. We have it move around different objects, and we are looking to 3D reconstruct those from just sonar measurements. So this is one of the test structures we have put together. To the right, there is a ground truth mesh that we scan by taking this object out of the tank and laser scanning it. And then by running differentiable rendering techniques that we've now extended to work with sonar, we can actually get very, very detailed reconstruction of this object, even though sonar doesn't actually produce any sort of localized measurements. And much more accurate measurements than previous techniques that try to either produce synthetic aperture measurements, basically focus on at different points, or use back projection techniques. So we can get millimeter accuracy 3D scans underwater, thanks in part to the fact that we can use this differentiable rendering technique to optimize our 3D shapes. I'll briefly mention one more setting, and this is a paper, this is joint work with Byung-Juan. Is Michael around? I don't see him here. And Ashin Sankaramarayanan at CMU. It's actually appearing here at CVPR, so you can go see the poster on Tuesday. So the idea is that we are trying to do very detailed objects of reconstructions of objects with complex visibility without having to spend a lot of time taking multi-view images of those objects. If you have complex visibility, you really need to have a lot of viewpoints to make sure that you image everything on your object. So instead of having a lot of cameras, a trick you can do is to use something called a kaleidoscope. It's a Greek word, but basically it means that put a lot of mirrors together and place your object inside. So if you do that, you will get an image like this, where in one image, you have baked into it a lot of viewpoints of the object, right, in a single shot. So here is a simulation of all of the views we have that correspond to the different cameras. And here are the different cameras that we have in these images, okay? So kaleidoscopic 3D imaging. Now, of course, it's not straightforward to try to solve this problem, because even though we have a lot of these views, they are all unlabeled. I don't necessarily know the camera they came from, and also don't know which pixel in the image corresponds to which view. So we have come up is with an algorithm that does both the 3D reconstruction and this labeling using differentiable rendering for the 3D reconstruction and some clever geometric reasoning, You can judge if it's clever or not, for the labeling to try and to solve this problem. And that's an example of the kind of 3D scans we can do over here, where by using these images and processing our pipeline, we can get very, very, very detailed 3D reconstructions of different objects. Okay? So those all 3D reconstruction examples. I will show one more case of one more use case for differentiable rendering that goes back to what Aditya was describing earlier in terms of gradient index optics. One problem we'll be looking into is how can we come up with optimized refractive index profiles, heterogeneous refractive index profiles, optimized for some specific lensing task. Now, to be able to tackle this kind of design now problem, this kind of inverse problem, we need to extend our differentiable rendering algorithm to account not just for global illumination, but also for the curving of light that Aditya also mentioned earlier that happens inside these materials. So I'll very briefly show you how this works. I have some slab of glass or some slab of material. There is a refractive index that changes from one location to another. If I shoot a ray through this ray will curve. So at every location will have effectively a velocity that corresponds to how fast the gradient index changes. And if I model this velocity using some differential equations that come from geometric optics, I will end up tracing a curved ray inside the material. Someone was asking about this earlier. These differential equations are exactly the Lagrangian version, if you want, of Fermat's principle, the principle of stationary points. Now, in practice, we cannot simulate these equations analytically, so we discretize them. We can break them into some step size, and that will give me a non-linear ray tracing process that allows me to travel from one point of the material to the other. Now, remember, what we want to do is differentiate this process with respect to some objective. So what is that objective? I may want, for example, a ray that's entering the medium on the left to arrive at some target point X that will correspond to the design of an object, right?
So I can set up a minimization problem like this, and I can now optimize this problem with respect to the refractive index of the material by doing gradient-based optimization. Do this gradient-based optimization, I'll differentiate this. And it turns out we can prove that I can do this differentiation effectively by running this nonlinear ray tracing process in reverse. So I can start here, go backwards, compute some gradient that will update my refractive index, keep going backwards, and I'll get to the start of the medium. At each one of these intermediate steps, I get some gradient term that updates my local refractive index, and then all of this process can be plugged in into a general differentiable renderer wherever I have to replace forward ray tracing with this nonlinear process. Again, there's a lot of math explaining why this works, but at a high level, all I have to do is just run the same nonlinear process backwards and use carry together with me gradients that I use to update the unknown refractive index. So I'll show you some of the example designs we can do with this. One is just to show you that this works to reproduce a lens that we actually know how to design from math. And this is called the Lüneburg lens. It was introduced by Lüneburg. I don't remember the exact date. I think it was sometime in the mid-20th century. And it's a lens that shows, I like this as an example because it shows why I would care to use green optics, gradient index optics. It produces a focusing capability that I cannot get with conventional refractive optics, with a lens that has just two refractive surfaces. So here's what it does. It takes a bundle of parallel rays and focuses all of them in the antipodal point. And now, if I rotate this, I will also focus a bundle of rays in the antipodal point. Effectively, I can think of this as a lens that at infinity doesn't have a planar focusing surface, but it has a spherical focusing surface. A conventional lens at infinity takes parallel bundles and focuses them all in a point in a plane. A Lüneburg lens focuses them on a sphere. That's a capability that I can only get, as far as I know at least, using gradient optics. And Lüneburg proved that in 1944 that if I make my refractive index profile have this specific expression, I will produce this kind of focusing capability. So can we reinvent this using differentiable rendering? We can set up an inverse problem where we say any ray, when it exits the medium, I want to get it to exit the X target, do differentiable rendering, and this is the optimization I get. I update my refractive gradients until I arrive at the refractive index field that matches the one that Lüneburg discovered analytically. So if I plot this, I see that the optimized profile and analytic match very, 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 very closely. Now, of course, that's just a demonstration. There is no reason to rederive this well-known design. But you can now start thinking about other tasks, other optimization tasks for other types of gradient indexed optics that are commonly used. One of them is optical fibers. There are two types of optical fibers. Ones where light just bounces around between two materials of fixed refractive index, and gradient index optical fibers, where the innermost tube of the fiber has a refractive index such that a ray will follow a curvy path that always stays inside the ray. This is a very commonly used kind of optical fiber, especially if you're using very monochromatic light and you're looking to propagate along very, 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 very long distances. The problem is that even though the rays always stay inside, they will end up having different phases. They will end up staying inside the fiber for different amounts of time. And this is a problem, an effect called modal dispersion. You can see it from the fact that as I input these rays, I get this messy diagram. If I didn't have modal dispersion, if all of the rays travel for the same amount of time inside the fiber, I would be seeing a pattern like this, where rays focus at intermediate points. So what can I do? I can set up an optimization problem that says, optimize this fiber so that I have no modal dispersion. And I can then solve this optimization problem using differentiable rendering. So this is the result. Here's how we optimize the refractive index profile of the fiber. And we end up with some final design that has much, much, much more improved modal dispersion compared to the original optical green fiber that we get from analytical expressions. Okay, and I can even visualize how good my focus at each one of these intermediate points. In our optimized design, we end up with a very, very low modal dispersion corresponding to this highly optimized focus point I see throughout the fiber something that I cannot do with the initial, I can only do because of the fact that I have available to me this differentiable rendering capability. Okay. So I'll show you one more kind of inverse problem we can solve in the context of green optics, multi-view displays. So I can say that given I have so many degrees of freedom available to me, I have a 3D volume of refractive indices I can play with. Can I do tasks such as the one I'm showing here? Build effectively a multi-view display where if light is coming in from the top, someone on the opposite side will see an image of Albert Einstein in this case. And if light is coming in from the left, someone standing on the other side of this display will see an image of Alan Turing. What is the refractive index I can use to do that? So I have no idea what this refractive index volume should produce. But I can set up a differentiable rendering model since I know how to differentiate all of these processes and end up with a design that looks like this. These are the optimization results. I end up getting very nice displays of these two images, and I end up producing effectively this nice multi-view display, static display in this case, but hopefully in the future, maybe with some of the stuff I presented earlier, potentially something that I can actually realize in real time. Okay. So I'll mention one more thing just to show you the fact that these differentiable rendering applications can have some real world impact. So we very recently started the project at CMU with Basti Serra and Katya Sikara, where we are looking to do wildfire monitoring. And the whole idea of this project is that we want to work with with firefighters, have drones move around fire plumes, and then there use differentiable rendering to tomographically reconstruct fire environments and use it to provide feedback. So that's a direct translation of differentiable rendering technology from computational image computer graphics to this very critical nowadays, and as everyone may have seen in Canada the last few weeks, becoming more and more important real world problem. All right, so I'll stop here. And we can switch to the outro. Are there any questions while we're transitioning?
Yeah, maybe. Thank you for the talk. It's just for curiosity. Like, do you see any application of this rendering being applied to astronomy?
Yeah, so I think in fact that Katie Bowman's work at Caltech, they are having some work on, I guess it depends on what kind of technology you are talking. I think they have been looking to use some, in fact, some of the differentiable rendering I saw at the very last with green optics for optimizing different astronomical parameters relating to black holes. I will admit I'm not super relevant with the physics. I think there is also more generally a potential for application there to deal with atmospheric turbulence, for example. That's a big problem when we do astronomy, with the fact that any kind of images we capture passively or even actively, they will get distorted by the fact that air has some atmosphere. So I think that there is definitely room to try to optimize the descattering techniques we have using both forward rendering and differentiable rendering. These are the two I'm familiar with. There's non-astronomy. Any other questions? You don't need to switch. You can just show my.
Oh, I switched already. Sorry.
Thank you.
Do you have the latest slides now?
Okay, everyone. So very quick take-home messages. First of all, what a great time to do imaging.
And open the camera from your laptop. Okay, go ahead.
Awesome. Thank you. Yeah, like I was saying, what a great time to do imaging instead of spending so many night outs in the lab building complicated systems. We can now use physics-based rendering to build to simulate all these complex imaging systems and do a software design of these imaging systems, not just intensity-based cameras, but also cameras such as time-of-flight cameras, sonar cameras, or tactile sensors with the help of physics-based rendering. We can also simulate previously ignored but super useful physics of light and matter interaction, such as continuous refraction, which makes light curve, or also render these effects, wave effects such as speckle that Yanis has presented. And what does all these new capabilities gives us? Well, a lot of things. Physics-based rendering systems can act as digital twins for scientific and engineering imaging systems, and hence help us in a variety of ways, including iterating on various hardware parameters virtually on computer before building or before coming up with the best design parameters that we can build the hardware on, or generate training data sets for deep learning techniques, or augment the existing data sets with the help of physics-based rendering. We showed how we can build imaging systems for various applications, including non-linear set imaging, acousto-optics, ultra-fast light scanning technique, imaging through scattering media, tactile sensor design, also green waveguide design, and so on. These physics-based rendering systems, like Yanis showed, they are also differentiable, and hence they allow us to incorporate, they can be incorporated into this general inverse problems with the help of analysis by synthesis approaches, which finds applications in underwater sonar, non-line of sight imaging, or green optic design that Yanis has shown in the second half.
So one thing I want to say here is that in this one. Key to all of these capabilities we have mentioned here is the fact that we can do not just rendering, but Monte Carlo rendering. It's really, I want to say that in all of these simulations, they can use the Monte Carlo nature that makes it possible for them to scale up to very complex scenes, scale up to very large scenes, and be very computationally efficient. So to try to generalize this kind of paradigm, what we have been looking into is how can we use Monte Carlo algorithms to simulate more and more and more general physics and sensing algorithms? And if you think about it, with Monte Carlo rendering, we are simulating just one PDE, the rendering equation. What we've been trying to think is, can I change that? Can I take Monte Carlo and now simulate the solutions of partial differential equations corresponding to a lot of other different effects, like Laplace, Poisson, and so on? And in fact, we have a couple of papers coming up at SIGGRAPH 2023 with Rohan Sohni, my student Bailey Miller, and Keenan Crane, where we show exactly that. We can generalize a lot of these algorithms that we use for Monte Carlo rendering of images to solve stuff such as diffusive heat transfer, oxygen flow, and other physical problems that are described by, in this case, Laplace and Poisson and screen Poisson PDEs. And the reason why we can do this much more efficiently, much more scalably, and much more robustly than before is exactly because we are switching from finite element-based reconstruction and simulation techniques to Monte Carlo techniques. So I want to emphasize the Monte Carlo part of all of this simulation work that Aditya and I presented.
Yeah, and with that, we conclude our tutorial on physics-based rendering and its applications to computational imaging. We want to thank several of our collaborators for their help in conducting this research, and various funding agencies, including NSF, DARPA, ONR, Sloan, AWS, and also an NSF Expeditions program, See Below the Skin, for their support. I will leave this slide here and open up stage for more questions. And also thank you all for your attention and questions so far, but we are also available here for more questions right now.
And just one other, we'll put the slides and references on the website and the tutorial is over. And the recording.
But using these techniques and open source rendering engine,
yeah, thank you, Pranit, for the question. All the simulators we have built, we have open sourced them. They are available both on our websites and also the CMU imaging group website.
And we'll include them in the references we post in the tutorial website. But yeah, they're all already available.
Yeah, yes, that's all.
All right.
Yeah, thank you all again.
Thank you. Yeah, I don't see any questions.